Please subscribe to support the channel. How big is the universe compared to our own Milky Way galaxy? It's a question that stretches the limits of human imagination. When we gaze at the night sky, every twinkling star we see belongs to our Milky Way, a vast spiral galaxy containing hundreds of billions of stars. Yet our galaxy is just one among billions, maybe trillions, scattered across the cosmos. The universe extends far beyond what we can ever see, with the observable part alone spanning about 93 billion light-years across. Compared to that, the Milky Way is a single glowing island in an endless ocean of galaxies, a mere speck in a cosmic expanse so vast that it defies comprehension. It reminds us how small we are, yet how extraordinary it is that we can even ask such a question. A galaxy is one of the universe's most majestic and complex creations. A colossal collection of stars, planets, gas, dust, and dark matter, all bound together by gravity in a cosmic dance that has lasted for billions of years. When we talk about a galaxy, we're not referring to something small or localized. We're speaking of a structure so vast that even light, the fastest thing in existence, can take tens of thousands of years to cross from one end to the other. At its heart, every galaxy is both a cradle and a grave for stars, a place where new suns are born out of clouds of gas, and where ancient stars burn out and collapse, enriching the galaxy with heavier elements that later become the building blocks of planets and life. What makes a galaxy so fascinating is not just its size or beauty, but its role as a fundamental building block of the cosmos. Without galaxies, there would be no organized structure in the universe, no clusters of stars, no planets, no life as we know it. In the earliest moments after the Big Bang, matter was spread out almost evenly, but tiny ripples in density allowed gravity to begin pulling matter together. Over hundreds of millions of years, those gravitational clumps grew, forming the first stars and, eventually, the first galaxies. These early galaxies were smaller and more chaotic than the elegant spirals we see today, colliding and merging over cosmic time to create the massive galactic systems we now observe. Galaxies come in a wide variety of shapes and sizes, each telling a story about its history. Some, like our Milky Way, are grand spirals, swirling disks with long, graceful arms that wind outward from a dense, star-packed core. Others are elliptical, vast balls of stars that lack defined structure, but contain some of the oldest stars in existence. Then there are irregular galaxies, whose chaotic shapes hint at past collisions or gravitational disruptions. These differences aren't just aesthetic. They reveal clues about how galaxies evolve, how they interact, and how gravity sculpts the universe on the largest scales. But what truly binds a galaxy together is gravity, the invisible hand that shapes everything from the smallest asteroid to the largest cluster of galaxies. Every star, every drifting cloud of gas, and every invisible particle of dark matter contributes to this gravitational pull, keeping the galaxy cohesive despite its internal motion. Dark matter, a mysterious form of mass that doesn't emit or reflect light, is particularly crucial. In fact, most of a galaxy's mass is made up of dark matter, not the visible stars or gas. Astronomers discovered this by studying how galaxies rotate. The outer regions spin much faster than they should if only visible matter were present. This unseen mass forms a vast invisible halo surrounding the galaxy, giving it the gravitational strength to hold itself together over billions of years. Within each galaxy, there exists a rich tapestry of environments. Some regions glow brightly with the light of new stars forming from collapsing clouds of hydrogen. Others are calm and quiet, filled with old stars nearing the end of their lives. Black holes, some millions or even billions of times more massive than our Sun, often lurk at galactic centers, devouring matter and shaping their surroundings through immense gravitational forces. The interplay of all these elements, gravity, star formation, stellar death, and dark matter, makes each galaxy a living, evolving system, constantly changing and adapting over cosmic time. The sheer scale of a galaxy defies normal understanding. To put it in perspective, our solar system, from the Sun out to the orbit of Neptune, spans about 4.5 billion kilometers. That sounds enormous, but it's almost nothing compared to a galaxy. Even a small galaxy might stretch across tens of thousands of light years. One light year, the distance light travels in a single year, is about 9.46 trillion kilometers. Multiply that by tens or even hundreds of thousands, and you start to glimpse just how vast a galaxy truly is. And remember, galaxies are not isolated. They exist in clusters and superclusters, bound together in an even grander web of cosmic structure. When astronomers peer into the deep sky using powerful telescopes, they don't just see stars, they see galaxies, countless ones, scattered across every patch of sky. In fact, if you were to point the Hubble Space Telescope at a seemingly empty region of space and let it collect light for days or weeks, what emerges is astonishing. Thousands upon thousands of faint galaxies, each one potentially holding billions of stars. It's a humbling realization that even the darkest patch of sky is teeming with galaxies beyond counting. Yet despite their immensity, galaxies are fragile in a way. They collide, merge, and transform. Over billions of years, these interactions reshape their structure. When two galaxies meet, their stars rarely collide directly. The space between stars is too vast. But their mutual gravity distorts and blends them into new forms. These galactic mergers can trigger waves of star formation, ignite active galactic nuclei, and even birth entirely new galaxies from the wreckage. The universe, in this sense, is both violent and creative, constantly recycling its matter, forging new systems from the remnants of the old. Understanding galaxies has been one of humanity's greatest scientific triumphs. For most of history, we thought the Milky Way was the entire universe. It wasn't until the early 20th century that astronomer Edwin Hubble discovered that the faint nebula observed in the sky were actually other galaxies far beyond our own. That revelation completely transformed our understanding of the cosmos. Suddenly, we realized that the Milky Way was just one galaxy among billions, each an enormous island universe in a vast and expanding sea of space. And among these countless cosmic islands, one stands out to us above all others: our own home, the Milky Way. It's the galaxy that nurtures our sun, our planets, and every living being that has ever existed. To truly understand how vast the universe is, we must first understand the scale and beauty of the Milky Way itself, the place that gave rise to life and to the consciousness capable of wondering about the universe's size. Our next step in this cosmic journey takes us there, to the great spiral that we call home. The Milky Way is our cosmic home, a magnificent spiral galaxy that cradles everything we know: the sun, the earth, and every living being that has ever existed. When we look up at the night sky and see that faint milky band stretching from horizon to horizon, we are looking toward the dense heart of our galaxy, peering across thousands of light years of stars, gas, and dust. That glowing river of light isn't just a collection of stars. It's a cross-section of the galaxy itself, a side view of the vast disk that we live inside. From our tiny vantage point, it seems like a thin ribbon across the darkness. But if we could step outside and see the Milky Way from afar, we would witness something far grander: a sprawling spiral galaxy, elegant and complex, with arms that coil outward from a brilliant central core. The Milky Way stretches roughly 100,000 light-years from edge to edge, which means that light, the fastest thing in the universe, would take 100,000 years to travel from one side of the galaxy to the other. Within that immense span lies an estimated 100 to 400 billion stars, each potentially surrounded by planets of its own. Our Sun is just one among them, an ordinary yellow star orbiting quietly in one of the galaxy's spiral arms, far from the bustling core. And yet, out of all those billions of stars, it is our Sun that warms a small blue planet, giving rise to oceans, forests, and thinking beings who can contemplate the galaxy scale.
The Milky Way's structure is that of a barred spiral galaxy, meaning it has a central bar-shaped region of stars from which its spiral arms emerge. This bar, about 27,000 light-years long, forms the heart of the galaxy, and beyond it, the arms wind outward in majestic curves. There are several major spiral arms, including the Perseus arm, the Sagittarius arm, and the Scutum Centaurus arm, along with smaller branches and spurs. Our own solar system sits within one of these smaller branches, known as the Orion arm or the Orion spur, a quiet region located about 27,000 light-years from the galactic center and roughly the same distance from the galaxy's outer edge. This position is remarkably stable and peaceful compared to the chaotic activity near the center, making it an ideal neighborhood for life to flourish. The galactic center itself is a place of extreme energy and mystery. At its very core lies a supermassive black hole called Sagittarius A, containing about 4 million times the mass of our Sun. Despite its invisible nature, its presence is undeniable. Stars near the core whip around it at incredible speeds, their orbits betraying the gravitational pull of an unseen giant. Surrounding this black hole is a dense concentration of stars, gas clouds, and cosmic dust, all bathed in intense radiation. The farther out you go from the center, the more the environment changes. The central bulge gives way to the flat disk of the Milky Way, where most of its stars, including our Sun, are found. Beyond that disk lies the galactic halo, a vast spherical region filled with old stars, globular clusters, and the elusive dark matter that makes up most of the galaxy's mass. What's truly astonishing is how dynamic the Milky Way is. Though it appears static to us, everything within it is in constant motion. Our solar system isn't fixed in space. It's orbiting the galactic center at an average speed of about 828,000 kilometers per hour. Even at that incredible velocity, it takes roughly 230 million years for the Sun, and everything orbiting it, to complete a single journey around the galaxy. In other words, the last time our solar system was in the same position, dinosaurs still roamed the Earth. The galaxy is like an enormous rotating wheel, with its stars and planets moving together in a graceful but relentless cosmic rhythm. And yet, despite all this movement, the Milky Way maintains its stunning spiral shape. That structure is sustained not by individual stars following the spiral arms like cars on a highway, but by waves of gravitational density that ripple through the disk. As these waves pass through, they compress gas and dust, triggering bursts of star formation. The bright young stars that form within these regions light up the arms, making them glow more vividly than the surrounding space. Over time, the arms themselves appear to rotate, but in truth, they're more like standing waves, patterns that persist as stars move in and out of them. It's an elegant balance of motion and structure, a kind of galactic choreography that has been unfolding for billions of years. The Milky Way's disk is also incredibly thin compared to its width. It's only about 1,000 light-years thick, a mere sliver compared to its 100,000 light-year diameter. If the galaxy were scaled down to the size of a dinner plate, the disk would be thinner than a sheet of paper. Yet within that slim plane lies nearly all of its luminous matter. Countless stars, nebulae, star clusters, and planetary systems. Interstellar gas clouds drift between the stars, providing the raw material for new generations of suns. Supernovae, the explosive deaths of massive stars, pepper the galaxy with heavy elements, seeding future stars and planets with the ingredients for life. The Milky Way, in this sense, is not just a structure, but a living, breathing ecosystem on a cosmic scale. Surrounding the visible galaxy is something even larger and more mysterious: the dark matter halo. This invisible sphere extends far beyond the outermost stars, possibly as far as several 100,000 light-years. Although we cannot see it directly, its gravitational influence shapes the motion of the entire galaxy. Without dark matter, the Milky Way could not hold itself together. Its outer regions would spin apart. This unseen mass, which makes up most of the galaxy's total weight, reminds us how little we truly understand about the fundamental nature of the cosmos. We live inside a galaxy that is both familiar and profoundly enigmatic, one that nurtures us yet hides most of its secrets in darkness. When astronomers map the Milky Way, they do so indirectly, since we're inside it and can't view it from above. It's like trying to draw a picture of your own house while standing in one of its rooms. Using radio waves, infrared light, and other forms of radiation that can penetrate interstellar dust, scientists have pieced together a remarkably detailed picture of our galaxy's shape and structure. They found massive molecular clouds where stars are forming, ancient star clusters orbiting far above the disk, and streams of stars left behind by dwarf galaxies that were long ago absorbed into the Milky Way. Each discovery adds another layer to the portrait of our galactic home, showing it to be not just a collection of stars, but a dynamic, ever-changing cosmic city. And just as our galaxy contains billions of stars, it likely contains hundreds of billions of planets. Many of these worlds orbit in stable systems much like our own, and some of them may host conditions suitable for life. It's a staggering thought. Scattered throughout the spiral arms of the Milky Way could be countless worlds where other forms of life, perhaps even other civilizations, look up at their skies and wonder about their place in the galaxy. The Milky Way, vast and ancient, may be filled with life and intelligence that we have yet to discover. As we continue our journey outward, the scale of the Milky Way gives us a reference point, a foundation for understanding what lies beyond. Because as enormous as our galaxy is, it is far from unique. All across the universe, galaxies like ours, spirals, ellipticals, and irregulars, drift through space in numbers beyond imagination. The Milky Way is just one shining island in a cosmic sea of billions, each with its own story, its own stars, and perhaps its own observers wondering the same thing we do. To appreciate how vast the universe truly is, we must now take another step back and understand the unit of measure that defines these enormous distances, the light year. It's a term that's often mentioned in astronomy, but it's also one that's easily misunderstood. Many people assume it's a measure of time, but it's not. A light year is a measure of distance, specifically the distance that light travels in 1 year. Because light moves incredibly fast, about 300,000 kilometers per second, that distance adds up to a staggering number, approximately 9.46 trillion kilometers, or about 5.88 trillion miles. When astronomers describe something as being 10 light years away, they mean that the light from that object takes 10 entire years to reach us, crossing billions upon billions of kilometers of empty space before finally entering our eyes or the detectors of our telescopes.
To put that into perspective, think about sunlight. The sun is about 150 million kilometers away from Earth, and the light it emits takes a little over 8 minutes to reach us. That means every time you look at the sun's glow, or more safely at sunlight shining off a wall or through the clouds, you're actually seeing the sun as it was 8 minutes ago. The moon, by contrast, is roughly 1¼ light seconds away. So the light we see from it left the lunar surface about a second before it reaches our eyes. When we look at the stars in the night sky, the distances become far more profound. The nearest star to our sun, Proxima Centauri, is about 4.24 light years away. That means the light we see from it tonight actually began its journey more than 4 years ago, before the last Olympics, before recent memories, before countless human moments we've already forgotten. Every star is a time capsule, its light carrying a message from the past. Now, imagine scaling that up to the size of our galaxy. The Milky Way is about 100,000 light years across. That means if a beam of light were to start at one end and travel to the other at full speed, the fastest speed possible in the universe, it would take 100,000 years to make the trip. For comparison, 100,000 years ago, early humans were still painting the walls of caves and sharing the planet with woolly mammoths. The concept of a light year connects space and time in a way that's almost poetic. Distance becomes time, and every corner of the cosmos becomes a glimpse into history. The farther away something is, the older the light we see from it. When astronomers observe galaxies millions or even billions of light years away, they're not seeing those galaxies as they are now. They're seeing them as they were millions or billions of years ago.
The night sky, in that sense, isn't a snapshot of the present, it's a vast, living record of the past. The light year also helps us comprehend how utterly vast space really is. Take our solar system, for example. The farthest human-made object, the Voyager 1 spacecraft, launched in 1977, is traveling at about 17 kilometers per second, faster than any commercial aircraft or missile. Yet even after nearly 5 decades of continuous flight, Voyager 1 is still less than 0.002 light-years from Earth. It hasn't even made it past a fraction of a single light-year. To reach the nearest star at Voyager's current speed, it would take over 70,000 years. The speed of light, therefore, isn't just fast, it's unimaginably fast. And yet, even at that speed, distances in the universe are so enormous that light takes thousands, millions, or even billions of years to cross them. When astronomers use light years, it's not just for convenience. It's because normal units like kilometers or miles become meaningless at cosmic scales. Saying that the Andromeda Galaxy is 24 quintillion kilometers away doesn't really tell us much. But saying it's 2.5 million light-years away immediately tells us something powerful. The light we're seeing from it tonight began its journey long before humans existed as a species. When that light first left Andromeda, the earliest ancestors of modern humans were still learning to use simple tools. The night sky, in that sense, is both a map of space and a window into time. Every point of light represents a story from the past traveling across the vacuum of the cosmos to finally reach our world. Light, though weightless and intangible, is the great messenger of the universe. It carries with it the history of everything, from the faint glow of distant galaxies to the radiation that lingers from the birth of the universe itself, known as the cosmic microwave background. The moment we detect light from a distant object, we are literally touching the past. This is why astronomy is sometimes called the archaeology of light. Unlike archaeologists who dig into the Earth to uncover sentient civilizations, astronomers dig into the cosmos by capturing ancient light. Every photon that reaches our telescopes has spent centuries, millennia, or eons crossing the cold darkness of interstellar and intergalactic space to tell us a story about where it came from. But to truly appreciate what a light year means, we must confront its implications. The speed of light isn't just a useful measuring stick, it's also a limit. According to Einstein's theory of relativity, nothing can travel faster than light in a vacuum. This limit sets a boundary on how far we can explore, communicate, or even influence the universe. If we were to send a signal today to a civilization 100 light-years away, they wouldn't receive it until the year 2125. And if they replied instantly, we wouldn't hear back until the year 2225. In the grand scale of the cosmos, light years remind us that the universe is not only vast, but also slow to reveal its secrets. Time and space are woven together so tightly that looking outward means looking backward. Even within our own galaxy, light years become essential for expressing distances. The diameter of the Milky Way, 100,000 light years, is already far beyond the scale of human comprehension. Between individual stars, the average separation is about 5 light-years. That means even our nearest stellar neighbors are separated by gaps of billions of kilometers of empty space. When you consider that our galaxy alone holds hundreds of billions of stars, each surrounded by vast light-year stretches of emptiness, it becomes clear just how lonely and immense the cosmos really is. Space is not crowded, it's mostly nothing. A thin sprinkling of matter across an incomprehensible void. The light year bridges our imagination to reality. It's the ruler that allows us to translate the language of the universe. Without it, the distances between stars and galaxies would be incomprehensible, numbers so large they'd lose all meaning. With it, we can begin to construct a mental map of the cosmos, one that stretches from the warmth of our sun to the cold glow of galaxies billions of light years away. It allows us to appreciate that when we gaze upward, we are not just looking into space, but into history itself, witnessing light that has traveled across ages to reach our eyes.
Understanding the light year changes how we perceive everything in the universe. It's the key that unlocks scale, perspective, and even humility.
Because once you comprehend what a light year truly represents, 9.46 trillion kilometers multiplied again and again across the cosmos, you begin to realize that the Milky Way, enormous as it seems, is just a single page in an endless cosmic library. Each light year is a measure of not only distance, but also of time, wonder, and the incredible patience of the universe itself. And now that we've built this sense of scale, we can turn our focus back to our own place within this grand structure, to the small region of the Milky Way where our solar system quietly drifts, orbiting within one of its graceful spiral arms. Our solar system occupies a humble and relatively quiet corner of the Milky Way, a small neighborhood far from the bustling, star-packed core and the chaotic outer reaches of our galaxy. In the grand structure of the Milky Way, we are not near the center, nor are we on the very edge. Instead, our sun and its planets sit nestled within a small, unassuming region called the Orion Arm, sometimes referred to as the Orion Spur. This spur is a minor branch, situated between two of the galaxy's major spiral arms, the Sagittarius Arm on one side and the Perseus Arm on the other. From our vantage point here, we orbit calmly around the galactic center, surrounded by hundreds of billions of other stars that form the glowing disk of the Milky Way. Our location, roughly 27,000 light-years from the galactic center and about 26,000 light-years from the outer edge, places us in what astronomers often describe as a suburban region of the galaxy. Not too crowded, not too empty, and far from the most dangerous areas. This position, as unremarkable as it may seem, is actually quite special. The inner regions of the Milky Way, near the core, are densely packed with stars, radiation, and cosmic activity. Supernovae erupt frequently, black holes lurk in greater numbers, and clouds of high-energy particles make it a far less stable environment for planets and life. The outer regions, by contrast, are sparse and cold, with fewer heavy elements necessary for forming rocky worlds. Our solar system's placement strikes a delicate balance between safety and opportunity. Close enough to regions where stars have produced the elements we need, yet far enough from the galactic center to avoid destructive cosmic events. The Sun, like all stars in the galaxy, is in motion. It travels at an astonishing speed, roughly 828,000 kilometers per hour, as it orbits the Milky Way center. Yet, even at that speed, it takes about 230 million years to complete a single orbit. This means that since the Sun first formed, about 4.6 billion years ago, it has only made about 20 trips around the galaxy. In that time, the Milky Way itself has continued to evolve, its arms shifting and its stars forming and dying in an endless cycle of creation and destruction. Our planet, therefore, doesn't just orbit the Sun, it also rides along with the Sun, moving through the galaxy like a passenger on a vast cosmic carousel. If we could see the Milky Way from above, if we could step outside it and look back, our solar system would be almost impossible to spot. The Sun, though bright to us, is an ordinary G-type star, and it would blend in with countless others in the spiral arms. Even if you knew exactly what to look, it would be like trying to find a single glowing grain of sand on an entire beach. Yet, from this modest location, life has managed to emerge, evolve, and develop the capacity to look outward and ask where it came from. It's a testament to how extraordinary the ordinary can be. That from an average star in an average arm of an average galaxy, something as rare and complex as consciousness has arisen. From our place in the Orion Arm, the night sky reveals our galactic surroundings in subtle but beautiful ways. When you see the dense band of the Milky Way stretching across the night sky, you're looking toward the plane of our galaxy, the disk filled with billions of stars. The center of the Milky Way lies in the direction of the constellation Sagittarius, which is why that region of the sky appears richer and brighter. When you look away from the galactic plane, the number of visible stars thins out, giving way to darker stretches of sky dotted with faint, distant points of light. This view, though breathtaking, is only a tiny fraction of the whole. From our limited vantage point within the disk, we can't see the full spiral shape of our galaxy. We can only infer it through careful observation, mapping, and analysis of light from the stars around us. The region we inhabit is also shaped by the local gravitational influences of nearby stars and interstellar clouds. The Sun is currently passing through a small pocket of low-density gas known as the local bubble, a cavity carved out by ancient supernova explosions millions of years ago. This bubble stretches for hundreds of light years and contains the Sun and a handful of nearby stars, including Alpha Centauri, Sirius, and Procyon. Beyond the local bubble lies the local interstellar cloud, another region of diffuse gas through which our solar system is currently drifting. These structures are like weather patterns in the galaxy, immense, slow-moving flows of material that subtly influence the environment around us. In this vast galactic framework, our solar system feels incredibly small. From the outermost reaches of Neptune's orbit to the icy frontier of the Oort cloud, the distant show of comets that surrounds our solar system, we barely occupy a fraction of a light year. The entire domain of our sun's influence, the heliosphere, extends less than 2 light years at most, and beyond that, the interstellar medium of the galaxy begins. The Milky Way's disk, by comparison, spans 100,000 light years. To travel from our solar system to the nearest star, Proxima Centauri, light itself takes more than 4 years. And at the speed of our fastest spacecraft, the journey would take tens of thousands of years. In other words, we are confined to an extremely small neighborhood within a galaxy that is almost incomprehensibly vast. And yet, this tiny neighborhood holds immense meaning for us. It's here, in this quiet spiral arm, that our sun was born. About 4.6 billion years ago, a giant molecular cloud of gas and dust collapsed under its own gravity, ignited nuclear fusion, and became the star we now call the Sun. Around it, leftover material formed planets, moons, asteroids, and comets, the building blocks of our solar system. Every atom in our bodies, every element that makes up Earth, was forged in ancient stars that lived and died long before the Sun existed. Their remnants mixed into the cloud that formed our system, which means that, in a sense, we carry the history of the galaxy within us. The iron in your blood and the calcium in your bones were born in the hearts of stars that once shone somewhere in this very galaxy, perhaps thousands of light years away.
Our solar system's position also affects what we can see of the cosmos. Being located within one of the spiral arms means that our view of the galaxy's structure is partially obscured by interstellar dust. This dust scatters and absorbs visible light, making certain regions opaque to optical telescopes. However, using radio, infrared, and X-ray observations, astronomers can peer through the dust and map the hidden structure of the Milky Way. These studies reveal star-forming regions, clusters, and remnants of past supernovae, all of which contribute to the grand portrait of our galactic environment. The more we learn about where we are, the more we understand how interconnected everything in the galaxy truly is. It's easy to think of our location as insignificant, a small solar system tucked away in an ordinary arm of an ordinary galaxy. But that quiet stability may be exactly what made life possible here. In the inner galaxy, near the core, the density of stars would expose planets to constant bursts of radiation and frequent supernova explosions. In the outer regions, there might not have been enough heavy elements to form rocky planets or sustain complex chemistry. Our position, then, is like the Goldilocks zone of the galaxy. Not too hot, not too cold, not too crowded, not too empty. Just right for life to take hold and evolve into the thinking, feeling beings capable of contemplating all of this. So, here we are, orbiting a modest star in a spiral arm of a galaxy among billions, drifting through the Orion Spur like travelers in an endless cosmic ocean. From this vantage point, the night sky is not just a view. It's a map of our home in the universe, a reminder of how deeply connected we are to everything around us. And yet, even though we live within a galaxy teeming with stars, the spaces between those stars are unimaginably vast. To understand just how immense and lonely our galactic home can be, we must look closer at the distances separating our sun from even its nearest neighbors, the stars that share this arm of the Milky Way with us. When we think of the stars in our night sky, it's easy to imagine them as close companions, a glittering tapestry of lights all sharing the same celestial neighborhood.
Yet the reality is far more astonishing. Even the nearest stars to us are separated by distances so vast that they make our solar system seem like a microscopic speck adrift in an ocean of emptiness. Space, for all its beauty and the countless stars it holds, is overwhelmingly empty. The gaps between stars are so large that it's almost difficult to find the right words to describe them. What appears as a crowded sky to our eyes is in truth a sparse scattering of points across an incomprehensible void. Let's begin with our own closest neighbor, Proxima Centauri, a small red dwarf star located about 4.24 light-years from Earth. On a cosmic scale, that's next door. But in terms of distance, it's still staggering. 1 light-year equals 9.46 trillion kilometers, so Proxima Centauri is roughly 40 trillion kilometers away from us. To put that into human terms, if the sun were the size of a marble, Proxima Centauri would be another marble placed more than 700 kilometers away. Between them would be nothing but emptiness. No planets, no asteroids, no interstellar dust dense enough to see. Just the vast black vacuum of interstellar space. That's what separates even the closest stellar neighbors. Proxima Centauri isn't alone though. It's part of a triple star system known as Alpha Centauri, which includes 2 Sun-like stars, Alpha Centauri A and Alpha Centauri B, that orbit each other relatively closely, while tiny Proxima orbits much farther out. Despite being our nearest stellar system, the light from these stars is so faint that only the brighter pair, Alpha Centauri A and B, can be seen with the naked eye from the southern hemisphere. Their light takes more than 4 years to reach us, meaning that when you look at Alpha Centauri, you're seeing it as it was over 4 years ago. Even this close neighbor is unimaginably distant, so distant that no spacecraft built by humanity could reach it within many lifetimes. Our fastest probe, Voyager 1, moving at over 17 kilometers per second, would take more than 70,000 years to travel that far. That's longer than all of recorded human history. The next nearest star after Proxima Centauri is Barnard's star, about 5.96 light-years away. It's another red dwarf star, smaller and cooler than our sun, and while astronomically close, it's utterly unreachable with today's technology. Following that, we find other nearby systems like Wolf 359, Lalande 21185, and Sirius, the brightest star in our night sky. Sirius, though dazzlingly bright to our eyes, lies 8.6 light-years away, almost 82 trillion kilometers. That light shimmering in the sky left Sirius nearly a decade ago, long before many of today's conversations, conflicts, and discoveries even began. Every twinkling star we see is a message from the past, its light crossing immense stretches of nothingness before arriving here. When astronomers speak of the distances between stars, they often emphasize the sheer emptiness in between. Our solar system, with its planets, moons, and countless asteroids, occupies a region just a few billion kilometers across. Beyond the orbit of Neptune lies the Kuiper Belt, then the Oort cloud, a vast spherical shell of icy bodies that marks the outermost edge of the sun's gravitational influence. But even that enormous bubble extends less than 2 light-years from the sun. Beyond it, there is almost nothing until you reach the next star many trillions of kilometers away. If the sun were reduced to a small glowing dot in the center of a football field, the next star wouldn't appear until another football field stretched thousands of kilometers away. The Milky Way may contain hundreds of billions of stars, but they are so sparsely spread that on average, each star is separated from its neighbors by several light years, equivalent to trillions upon trillions of kilometers of empty space. And it's not just empty in terms of matter, it's empty in terms of energy and warmth too. The space between stars, called the interstellar medium, is composed mostly of tenuous gas and dust, just a few atoms per cubic centimeter. Compare that to the air you're breathing right now, which contains roughly 10 to the 25 molecules per cubic centimeter, and you begin to understand how unimaginably thin that medium is. Yet, even this nearly perfect vacuum isn't entirely empty. It contains traces of hydrogen and helium, tiny grains of cosmic dust and faint radiation left over from ancient stars and supernovae. These sparse materials form the raw ingredients for future generations of stars, drifting slowly through the galaxy until gravity gathers them into new stellar nurseries. This vast emptiness is one of the most humbling aspects of our universe. When you gaze up at the Milky Way on a dark night, you're looking across billions of stars, but the distance between each one is so immense that it makes the galaxy seem like a ghostly structure made mostly of nothing. Even if you could travel at the speed of light, you'd still spend years moving between one star and the next. If you were to set off from Earth and head towards Proxima Centauri at that impossible speed, you'd spend more than 4 years crossing a void so dark and silent that for most of your journey, you wouldn't pass a single object large enough to see.
The immense distances between stars have profound implications for the possibility of interstellar travel and communication. Any civilization, no matter how advanced, must contend with the limitations imposed by the speed of light. Even a simple exchange of messages between nearby star systems would take decades or centuries. For example, a radio signal sent from Earth to a planet orbiting Proxima Centauri would take over 4 years to arrive and another 4 to return. An 8-year conversation just to say hello and receive a reply. In this way, the universe enforces a kind of cosmic isolation, keeping each world and each civilization separated by gulfs of time and distance that make instant communication or travel impossible under known physics. And yet, despite the emptiness, the galaxy is not lifeless. Stars are scattered across space like tiny islands in a vast ocean, and each one may host planets, some barren, some gas giants, and perhaps some teeming with life. Our own sun is one of these countless stars, and around it orbits a world filled with oceans, mountains, and sentient beings capable of wondering about their neighbors across the void. That's the paradox of the Milky Way. It's both incredibly rich and overwhelmingly empty. The spaces between stars may span light years, but within those distances lie the possibilities for life, discovery, and wonder that have inspired humanity since the dawn of thought. To visualize how empty our galaxy really is, imagine shrinking the sun down to the size of a basketball. At that scale, Earth would be a tiny grain of sand about 30 meters away. The nearest star, Proxima Centauri, would be another basketball located more than 7,000 kilometers away, roughly the distance from New York to Rome. Every other star would be similarly spaced out, scattered across a volume of space so vast that even with billions of stars, the Milky Way would still be mostly darkness. The light you see in the night sky, the radiant band of our galaxy, is only visible because there are so many stars in that direction that their faint glow overlaps, like the collective light of distant cities seen from space. But if you were to travel out between those stars, you'd find yourself enveloped in near-perfect silence, surrounded by the endless black of interstellar space. And so, while our solar system is part of a grand spiral arm filled with stars, nebulae, and cosmic dust, the truth remains that the Milky Way is 99.9999999% empty. The stars that make it glow are like scattered embers across an infinite night, each one separated by unimaginable distances. Our galaxy's beauty lies not in its density, but in its delicate balance between matter and emptiness. A structure so vast that it holds billions of suns, yet so spacious that each one burns alone, a solitary beacon in a sea of nothing. This emptiness, however, is not the end of the story, because as we lift our gaze beyond our local stellar neighborhood, we begin to realize that our galaxy, this enormous, seemingly boundless structure we call home, is just one among countless others floating in the cosmic abyss. The Milky Way, magnificent as it is only a single island in a universe filled with billions of other galaxies, each one separated by even greater voids than those between stars. To understand how truly vast the universe is, we must now leave our home galaxy behind and look outward, toward the galaxies that lie beyond. When we finally step back from the boundaries of our own galaxy, that grand, spiral-shaped island of stars, gas, dust, and dark matter we call the Milky Way, a new and even greater truth begins to unfold. Our galaxy is not unique. It is not solitary. It is merely one among billions, perhaps even trillions of galaxies scattered across the cosmic abyss.
Each one, like the Milky Way, is a vast collection of stars and worlds, an entire realm of its own. The more we zoom out, the more our perspective transforms. What once seemed immense now becomes just one tiny piece in a cosmic mosaic so large that even our greatest telescopes can barely glimpse its edges. For much of human history, people believed that the Milky Way was the entirety of the universe. When ancient civilizations gazed up at the band of light stretching across the night sky, they imagined it as a river of milk, a pathway of spirits, or the glowing spine of the heavens. Even centuries later, scientists and astronomers still thought all of existence was contained in that hazy arc. The word galaxy itself comes from the Greek galaxias kuklos, meaning milky circle. It wasn't until the early 20th century that humanity began to realize just how mistaken that belief was. The Milky Way wasn't the universe. It was simply one galaxy among many. This revelation would become one of the most profound discoveries in human history. The turning point came in the 1920s when astronomer Edwin Hubble peered through the powerful telescope at Mount Wilson Observatory and observed distant, faint smudges of light that had puzzled astronomers for decades. Some called them spiral nebulae, believing they were swirling clouds of gas within our galaxy. But Hubble's careful measurements revealed something extraordinary. These nebulae were not within the Milky Way at all. They were entire galaxies in their own right, immense systems of stars located far beyond the borders of our own. The universe suddenly expanded in our understanding, from a single star system of stars to an unfathomable ocean filled with countless galactic islands. What was once thought to be everything turned out to be almost nothing in comparison to the greater whole. That realization shattered our sense of scale forever. The Milky Way, with its hundreds of billions of stars and its 100,000 light-year diameter, is immense, yet it's just one among billions. Every direction we look, the universe stretches farther and farther, revealing galaxies of all shapes, sizes, and compositions. Some are elegant spirals like our own, their arms gracefully winding outward from bright star-filled centers. Others are elliptical galaxies, massive and round, filled with older, redder stars. Still others are irregular galaxies, chaotic in form, shaped by the gravitational tugs and collisions of cosmic neighbors. Each galaxy tells a different story of birth, destruction, and rebirth across cosmic time. The diversity among galaxies is breathtaking. Some, like the giant elliptical galaxy IC 1101, dwarf even the Milky Way, spanning more than 5 million light-years across and containing over 100 trillion stars. Others, known as dwarf galaxies, are small and faint, sometimes containing only a few million stars. There are galaxies in the process of colliding, merging to form even larger systems, and galaxies drifting alone in the silent reaches of intergalactic space. Some harbor supermassive black holes at their centers, devouring matter and unleashing torrents of radiation that blaze across billions of light years. Others are quiet and dim, their stellar fires long faded. Together, they form the cosmic landscape, an immense tapestry woven from countless galactic threads. One of the most beautiful truths about these galaxies is that each one is a potential cradle of worlds. If our Milky Way alone contains hundreds of billions of stars, and many of those stars have planets, then across billions of galaxies, the number of possible worlds becomes unimaginably large. Every galaxy could contain trillions of planets, perhaps some rocky and warm like Earth, others frozen, gaseous, or alien beyond comprehension. Somewhere in those far-off systems, under foreign suns, there could be life, maybe even civilizations, wondering as we do whether they are alone in the vastness. The sheer number of galaxies multiplies the possibilities for life, for diversity, and for discovery beyond what our minds can comfortably hold.
The distances between galaxies, however, are even more daunting than those between stars. While stars within the Milky Way are separated by a few light years, galaxies are typically separated by millions of light years. The nearest large galaxy to us, Andromeda, lies about 2.5 million light-years away, a gap so vast that even light, traveling at 300,000 kilometers per second, takes 2.5 million years to bridge it. That means the light we see from Andromeda tonight
began its journey long before modern humans walked the Earth. When it left that galaxy, our ancestors were early hominids, using simple tools and fire for survival. So every time you gaze at Andromeda with the naked eye, faint but visible as a blurry patch in the night sky, you are literally looking back millions of years into the past. Galaxies, despite their enormous separations, are not scattered randomly through space. They are grouped into clusters and superclusters, forming a vast web-like structure across the cosmos. These connections hint at the underlying architecture of the universe, one that stretches far beyond what we can see. Between these immense structures lie vast cosmic voids, regions almost completely empty, spanning hundreds of millions of light years. The galaxies, then, are like bright pearls strung along invisible threads of gravity, forming an intricate and beautiful cosmic web that defines the shape of the universe itself. What's truly humbling is that, despite their staggering number, we've only observed a tiny fraction of all the galaxies that exist. The Hubble Space Telescope, by capturing a small patch of sky no larger than a grain of sand held at arm's length, revealed thousands of galaxies in that minuscule area alone. If that tiny speck of sky holds thousands, then the entire night sky must contain hundreds of billions of galaxies. Later, the James Webb Space Telescope pushed even deeper, uncovering galaxies that existed more than 13 billion years ago, relics from the infancy of the universe. These ancient galaxies are smaller, denser, and more chaotic than the majestic spirals we see today, offering a glimpse into the cosmic dawn when the first stars ignited and filled the darkness with light. Each of these galaxies, near or far, young or old, is part of a grand cosmic story, a story of structure, evolution, and time. The Milky Way is just one verse in that story, a familiar pattern in an endless cosmic poem. To stand beneath the stars and know that each pinprick of light belongs to a galaxy filled with billions of other stars is to confront the sheer enormity of existence. It's both humbling and exhilarating. We, who occupy a small planet orbiting an ordinary star, find ourselves living in one of countless galaxies scattered across an incomprehensibly vast universe. And yet, as we come to terms with this enormity, we find comfort in knowing that we have neighbors among the stars, not just nearby stars within our own galaxy, but entire galaxies themselves. The closest of these, our cosmic companion, is the Andromeda Galaxy, a massive spiral roughly the same size as our own Milky Way. It shines faintly in the night sky, quietly bridging the gap between us and the greater universe. And as we turn our gaze toward it, we take the next step outward in our journey to comprehend just how immense the universe truly is. The Andromeda Galaxy, known formally as Messier 31 or simply M31, is one of the most awe-inspiring celestial objects in the entire night sky. Not just because of its beauty, but because of what it represents. It is our nearest large galactic neighbor, a massive spiral system of stars, gas, and dark matter that mirrors the Milky Way in both size and structure. Andromeda is located about 2.5 million light-years away, which means that the light we see from it tonight began its journey toward us when early humans were just emerging as a species on Earth. Every time we gaze at Andromeda, visible as a faint, misty patch of light on a clear, dark night, you're literally looking back millions of years into the past, a vision of a galaxy as it was millions of years ago, long before the rise of modern civilization. To the naked eye, Andromeda appears subtle, almost ghost-like, a dim oval of diffused light that can easily be mistaken for a small cloud. Yet behind that delicate glow lies an immense galactic powerhouse. Astronomers estimate that Andromeda spans about 220,000 light-years across, making it slightly larger than our own Milky Way, which measures roughly 100,000 light-years in diameter. It contains somewhere between 1 trillion stars, more than twice the number found in our galaxy. Each of those stars could have its own family of planets, moons, and possibly life forms. When you think of Andromeda, you are not just looking at a distant smudge of light. You are looking at a vast realm of suns and worlds, a cosmic metropolis on a scale that dwarfs the imagination. Andromeda's structure is similar to the Milky Way's, a barred spiral galaxy with sweeping arms of stars and interstellar dust coiling around a bright central bulge. If we could see it up close, we'd behold lanes of dark dust tracing through glowing bands of blue and white stars, with massive star-forming regions illuminating the spiral arms like cosmic beacons. At its core lies a supermassive black hole, containing the mass of over 100 million suns, drawing nearby stars into fast orbits around it. This black hole is one of the key features linking Andromeda to the Milky Way, as both galaxies share similar central structures, immense gravitational hearts that shape their evolution over billions of years. But perhaps the most fascinating thing about Andromeda isn't just what it looks like, it's what it's doing. The Andromeda Galaxy is on a collision course with our Milky Way. Observations using the Hubble Space Telescope and other instruments have revealed that Andromeda is moving toward us at a speed of about 110 kilometers per second, roughly 250,000 miles per hour. Though space is so vast that the collision won't occur for another 4 to 5 billion years. When it does, the two galaxies will begin a slow, spectacular dance of gravitational attraction, merging into a single enormous elliptical galaxy, sometimes nicknamed Milkomeda or Milkdromeda. For billions of years, the stars of both galaxies will swirl together in grand tidal arcs, though few will actually collide directly as the distances between individual stars are so immense. It will be a breathtaking transformation, a cosmic event that will reshape our night sky forever. Even now, Andromeda and the Milky Way are not isolated. They are gravitational companions, linked as part of a small galactic neighborhood known as the Local Group. This group contains about 50 or so galaxies, most of them small, dwarf galaxies orbiting around the larger ones. In many ways, Andromeda and the Milky Way are like twin giants ruling over this cluster, their gravity binding smaller galaxies in a slow orbital waltz. The mutual pull between the Milky Way and Andromeda has already begun to subtly distort their outer halos of gas and dark matter, creating faint bridges of material that stretch through intergalactic space. Though the galaxies are separated by millions of light years, their destinies are already intertwined.
If you could travel across the space between us and Andromeda, you would traverse one of the most immense voids imaginable. It would take light 2.5 million years to make the journey, and at the speed of today's fastest spacecraft, it would take more than 40 trillion years to reach it, a time span thousands of times longer than the current age of the universe. Between us and that galaxy lies almost nothing, a near-perfect vacuum dotted only by the occasional rogue star, a drifting cloud of hydrogen, or the invisible haze of dark matter. And yet through this emptiness, light continues to travel, a silent messenger connecting our world to another colossal island of stars across the cosmic sea. The Andromeda Galaxy also holds deep scientific importance. Because it's relatively close by in cosmic terms, astronomers can study it in remarkable detail. By examining its stars, star clusters, and nebulae, scientists can learn not only about Andromeda itself, but also about the history and evolution of galaxies in general. Observations show that Andromeda, like the Milky Way, has a rich and dynamic history. It has absorbed smaller galaxies over billions of years, leaving behind stellar streams, long trails of stars stretching across its halo. These remnants of galactic cannibalism tell the story of how large galaxies grow through cosmic mergers, gradually building their size and structure by consuming smaller neighbors. One of the most striking things about Andromeda is that we can actually see it without any telescope. On a dark, clear night, far from city lights, you can look toward the constellation Andromeda, named after the mythical princess from Greek mythology, and spot it as a faint blur in the sky. That faint light, barely visible to the naked eye, has traveled millions of years through space, carrying with it the history of countless suns and worlds. To see it is to experience something profound. You are not looking at a nearby object, or even something within our galaxy. You are seeing across the intergalactic void into another galaxy entirely. It is one of the few deep sky objects visible without optical aid, a reminder of the scale of the universe and our small but miraculous ability to perceive it. The Andromeda Galaxy also offers a glimpse into our cosmic future. When it and the Milky Way finally merge, the night sky will change beyond recognition. Over the course of billions of years, Andromeda will grow larger and brighter in our sky, transforming from a faint blur to a vast glowing disk of light. Eventually, the two galaxies will pass through each other, their spiral arms twisting and stretching into immense tidal streams. New stars will ignite in bursts of stellar creation, fueled by the collision of interstellar gas. From any surviving planets, the night sky will blaze with the light of millions of stars, a cosmic fireworks display unfolding over eons. And after the chaos settles, a new, massive elliptical galaxy will remain, a monument to the forces of gravity and time that shape the cosmos. In the grand tapestry of the universe, Andromeda is both a mirror and a messenger. It reflects what our galaxy is, a spiral system filled with stars, dust, and life, and it hints at what we might become. It tells us that galaxies are not static or eternal, but living systems that grow, evolve, and merge over cosmic time. Its light, which began its journey millions of years ago, now whispers to us of vast distances, ancient stars, and the inevitable dance of creation and destruction that defines the universe. Andromeda stands as a bridge between the familiar and the infinite. It reminds us that even though we inhabit just one galaxy, we are part of a far greater story, a story that stretches across millions of light years and billions of years of cosmic history. And as we lift our gaze from this neighboring giant to the broader cosmos, we begin to see that Andromeda and the Milky Way are not alone. Together, they belong to a family of galaxies, a small cluster floating within an even grander cosmic structure known as the local group, the next step in our journey through the universe. When we take another step back from the intimate cosmic connection between the Milky Way and Andromeda galaxies, our perspective expands to reveal a broader neighborhood, a collection of galaxies bound together by the gentle but unyielding pull of gravity. This collection is known as the local group, a small galactic cluster that serves as our cosmic home within the vast universe. It's a kind of celestial community, where the Milky Way and Andromeda act as the two dominant members, surrounded by dozens of smaller, fainter galaxies orbiting them like tiny satellites around giant worlds. While local might sound modest, the local group itself spans about 10 million light-years across, a region so immense that even light, traveling at 300,000 kilometers per second, would take millions of years to traverse from one side to the other. The local group contains roughly 50 to 60 galaxies, though most of them are far smaller and dimmer than either the Milky Way or Andromeda. These smaller galaxies are known as dwarf galaxies, and they come in a variety of forms. Some are irregular, shapeless clouds of stars, while others are tiny elliptical systems with barely a few million suns. Together, they form a kind of cosmic cluster where gravity maintains a delicate balance. Each galaxy follows its own orbit, yet all are held within the greater gravitational field that binds the group as one. At the heart of the local group are its two great spiral galaxies, the Milky Way and Andromeda, which dominate the group in both size and mass. They're like two grand cities in a vast intergalactic countryside, their gravitational influence extending far into the surrounding space. A third, smaller spiral galaxy called the Triangulum Galaxy, Messier 33 or M33, plays a supporting role. Though it's only about 60,000 light-years across, roughly half the size of the Milky Way, it's still massive enough to stand out among its many dwarf companions. The Triangulum Galaxy lies about 2.7 million light-years away from us, and is gravitationally linked to Andromeda, possibly orbiting it as a satellite galaxy. These three, the Milky Way, Andromeda, and Triangulum, form the backbone of the local group, anchoring its structure and defining its overall shape. Surrounding these larger galaxies are dozens of smaller ones, faint ghost-like companions that orbit the larger systems, much like moons orbit planets. The Milky Way alone is known to have at least 50 satellite galaxies, including the well-known Large Magellanic Cloud, LMC, and Small Magellanic Cloud, SMC, which are visible to the naked eye from the southern hemisphere. These two irregular dwarf galaxies are among our closest neighbors, located roughly 160,000 and 200,000 light-years away respectively. They are bound to the Milky Way by gravity and are slowly being torn apart, their stars and gas stretched into long tidal streams as our galaxy's immense gravitational field pulls them inward. Over billions of years, they may eventually merge with the Milky Way, contributing their stars to our galactic population.
Andromeda, too, has its own retinue of smaller companions. Some of its better-known satellite galaxies include M32 and M110, both elliptical dwarfs that orbit close to Andromeda's disk. These smaller galaxies, like cosmic siblings, dance around their larger host in slow, elliptical orbits that take billions of years to complete. In fact, many dwarf galaxies in the local group are believed to have been captured by the gravitational fields of either the Milky Way or Andromeda, drawn in from the surrounding space over cosmic time. Others, meanwhile, drift more freely, lingering on the outskirts of the group in tenuous gravitational orbits. The local group, while small in comparison to the immense structures that fill the universe, represents a microcosm of cosmic evolution. Within it, we can observe all the major stages of galactic life. We see young, active galaxies where new stars are still forming, like the Triangulum Galaxy. We see older, quieter systems, such as the dwarf ellipticals, whose star formation ceased billions of years ago. And we see the early stages of galactic interaction and merger, a process that will one day culminate in the union of the Milky Way and Andromeda, transforming the local group forever. This variety makes our local galactic cluster an invaluable laboratory for astronomers seeking to understand how galaxies grow, age, and influence one another. Despite containing dozens of galaxies, the local group is still mostly empty space. If you were to compress all of its galaxies into a single volume, they would occupy only a minuscule fraction of the total space available. The rest would be pure vacuum. Between the Milky Way and Andromeda lies about 2.5 million light-years of near-perfect emptiness, and beyond that, more void stretching toward the other members of the group. The gravitational bonds between these galaxies are faint, but over cosmic timescales, they're enough to keep the entire structure together. It's a kind of loose cosmic family, slowly evolving under the pull of its own collective gravity. One of the remarkable things about the local group is that it's not static, it's dynamic and ever-changing. Galaxies within it move, drift, and interact. Some of the dwarf galaxies orbiting the Milky Way are being shredded apart, leaving behind stellar streams, long, ribbon-like trails of stars that arc across the night sky. These streams are the remains of once independent galaxies that have been cannibalized by larger systems. In fact, both the Milky Way and Andromeda have grown over billions of years by consuming smaller galaxies, an ongoing process that continues even now. This slow cosmic feeding shapes the structure and composition of galaxies, demonstrating that even at this local scale, the universe is constantly in motion. The boundaries of the local group are defined by a kind of gravitational border known as the zero-velocity surface, the point where the expansion of the universe begins to overcome the gravitational attraction of the group. Inside this region, the galaxies remain bound together, orbiting one another in slow, intricate patterns. Beyond it, space continues to expand and galaxies drift away with the general flow of the cosmos. This boundary marks the edge of our gravitational neighborhood, separating our local cluster from the vast structures beyond. In the grand cosmic hierarchy, the local group is just one of many such clusters scattered throughout the universe. These small clusters often gather together into even larger formations known as superclusters, which form the scaffolding of the cosmic web. Our local group, for instance, belongs to a larger structure called the Virgo Supercluster, which itself is just one of many clusters interconnected across the cosmos. But before we journey that far outward, it's worth appreciating what the local group represents: a snapshot of the universe on a humanly understandable scale, not infinite, but still immense beyond imagination. The local group is our cosmic address in the universe, a way to describe where we fit into the grand structure of everything. If you were to write it like a postal address, it might go something like this: Planet Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea, Observable Universe. Each level of that address expands our perspective outward by orders of magnitude. Each step away from our home world reveals another layer of structure, another tier of cosmic order. The local group is our first true glimpse into the universe as a web of interconnected galaxies, vast distances bridged by gravity, light, and time. It's the family to which our galaxy belongs, a collection of stellar cities drifting together through the darkness. And as we continue to pull back even further, we begin to see that the local group itself is just a small node in a much grander system, a tiny thread in a colossal tapestry of galaxies, bound into enormous clusters. The next step in our journey takes us into that broader realm, to a structure so large and dense it makes even our entire local group look minuscule by comparison. The Virgo Supercluster, the next cosmic layer of our universe. When we step back yet again from the local group, our modest neighborhood of a few dozen galaxies drifting through space, we begin to perceive a grander and far more magnificent structure, the Virgo Supercluster. This colossal region of the cosmos is not a single cluster of galaxies, but a vast network of them, an immense web of matter stretching across tens of millions of light years. Within this supercluster lies the local group, quietly orbiting in one of its outer suburbs, like a small town on the edge of a sprawling cosmic metropolis. The Virgo Supercluster contains thousands of galaxies, organized into groups and clusters bound together by gravity, all moving in a slow, intricate ballet across the universe. It is here that our understanding of scale once again expands, and the immensity of the universe reveals itself in a new, almost incomprehensible dimension.
At its heart lies the Virgo cluster, the massive central concentration of galaxies that gives the entire supercluster its name. The Virgo cluster itself is enormous, spanning about 10 million light-years across and containing over 2,000 galaxies of all shapes and sizes, spirals, ellipticals, and irregulars, glowing with the combined light of trillions of stars. This cluster resides roughly 54 million light-years away from Earth in the direction of the constellation Virgo. Within it, some galaxies are true giants, containing hundreds of billions of stars, while others are faint dwarves, barely visible against a background of intergalactic space. The cluster is so rich in galaxies that, when viewed through a telescope, it fills the field of view with countless smudges of light, each one a vast island universe of its own. But the Virgo supercluster is much larger than the Virgo cluster alone. It extends outward for about 110 million light-years in diameter, encompassing dozens of smaller galaxy clusters and groups, including our own local group. The galaxies and clusters within the supercluster are not randomly scattered. They are arranged in an intricate web-like pattern, connected by vast filaments of galaxies separated by immense cosmic voids. These filaments act like the strands of a colossal spiderweb, stretching across intergalactic space and forming the scaffolding of the universe itself. In between them lie immense regions of emptiness, where few galaxies exist at all. Dark, silent expanses hundreds of millions of light-years wide. Within this structure, our local group is one of the many smaller groups located on the outskirts of the Virgo supercluster. Though we are gravitationally bound within the supercluster's domain, we are far from its dense, crowded center. We, along with neighboring groups of galaxies, are slowly moving toward the heart of the Virgo cluster, pulled by its immense gravitational influence. This motion, known as the Virgo infall, is a gentle drift by cosmic standards, but it's part of the vast, interconnected flow of galaxies across space. Every galaxy in the supercluster is participating in a slow, majestic movement,
drawn together by gravity, yet simultaneously carried apart by the expansion of the universe itself. The galaxies within the Virgo supercluster vary immensely in size, composition, and brightness. There are massive elliptical galaxies like M87, located near the cluster's core, which harbors a supermassive black hole with a mass of billions of suns, the same black hole famously imaged by the Event Horizon Telescope in 2019. Around these giant galaxies swarm countless smaller ones, interacting through gravitational forces that shape their evolution. Some collide and merge, triggering bursts of star formation. Others are stripped of gas as they fall into the cluster's dense environment, their star-making material torn away by gravitational tides and intergalactic winds. The Virgo cluster is a dynamic environment, full of motion, energy, and transformation, a place where galaxies live, die, and are reborn. Beyond Virgo's central cluster lie many other galactic families that together make up the broader supercluster. Astronomers have identified several major subgroups within it, including the Leo cluster, the Fornax cluster, and the Eridanus group, among others. Each of these regions contains hundreds of galaxies, and together they trace the immense, sprawling outline of the Virgo supercluster. What's truly remarkable is that all of these structures are gravitationally connected, yet still participate in the cosmic expansion, meaning that while gravity binds galaxies together on local scales, the universe as a whole continues to stretch, causing distant clusters to drift further apart over billions of years. The Virgo supercluster was once thought to be the largest structure in which our galaxy participated. For decades, astronomers believed it represented the upper boundary of cosmic organization, the grandest known arrangements of galaxies in the universe. But as observational technology improved, and telescopes like Hubble and later the Sloan Digital Survey mapped vast swaths of the cosmos, a new understanding emerged. The Virgo supercluster was not alone. It was merely one branch of an even larger structure, a colossal interconnected complex that extended far beyond what astronomers had previously imagined. That larger system would eventually come to be known as the Laniakea Supercluster. But before we reach that revelation, it's worth pausing to reflect on what the Virgo supercluster represents. To comprehend its sheer scale, let's attempt a comparison. If the Milky Way were the size of a single grain of sand, then the entire Virgo supercluster would stretch across hundreds of kilometers, a landscape filled with thousands of tiny grains, each one representing a galaxy. The distances between those grains would still be vast, separated by what, in this analogy, might be kilometers of empty air. Yet in that emptiness, every grain would be gravitationally linked to others, moving together as part of an immense cosmic system. The Virgo supercluster is not just a static structure frozen in space. It's alive with motion, energy, and change. Its galaxies orbit, merge, and evolve over cosmic time, weaving together the story of the universe's ongoing creation. From our perspective on Earth, located in one of the spiral arms of a modest galaxy in the outskirts of this supercluster, we see only a small slice of this grandeur. But through powerful telescopes and careful measurement, astronomers have charted the positions and motions of thousands of galaxies, mapping out the Virgo supercluster like a cartographer mapping continents on a newly discovered planet. And what they found is a universe that is both vast and beautifully ordered, a cosmic web where superclusters like Virgo are the continents, connected by filaments of galaxies and surrounded by immense voids, the cosmic oceans. It's humbling to realize that our entire local group, with its 50-some galaxies, including the Milky Way and Andromeda, occupies a space so tiny within the Virgo supercluster that it's almost negligible. If the Virgo supercluster were a massive city, our local group would be a single household on the far edge of town. Yet even from this distant outpost, we are connected to everything else within it by gravity, by light, and by the shared history of cosmic evolution that began nearly 14 billion years ago with the Big Bang. And so from our place within this immense galactic framework, the Virgo supercluster stands as a kind of cosmic bridge between the familiar and the unimaginable. It shows us that the universe is structured not randomly, but hierarchically. Galaxies form groups, groups form clusters, and clusters come together into superclusters.
Each level of this structure reveals a new layer of organization, a new scale of existence that dwarfs the one before it. The Virgo Supercluster is not the end of that hierarchy. It is merely another step along the path to understanding the full architecture of the cosmos. Because beyond even the Virgo Supercluster lies something even more extraordinary. A structure so vast, it redefines our understanding of the universe's size and shape. This immense region, stretching over 500 million light-years, is known as the Laniakea Supercluster, the true cosmic continent to which the Virgo Supercluster belongs. It is there, in the next step of our exploration, that we will finally begin to see just how immense the universe truly is and how small, yet deeply connected, our home galaxy is within it. When we pull the lens back even further, far beyond the Virgo Supercluster with its thousands of galaxies and colossal filaments of matter, an even grander cosmic architecture begins to take shape. The Virgo Supercluster, enormous though it is, turns out to be just one small piece of a still larger structure, a vast continent of galaxies that stretches across the universe like a celestial landmass. This immense system is known as the Laniakea Supercluster, a word derived from the Hawaiian language meaning immense heaven. And that name could not be more fitting, because Laniakea is among the largest structures ever mapped in the observable universe, an expanse of interconnected galaxies stretching over 500 million light-years from end to end, containing hundreds of thousands of galaxies and trillions upon trillions of stars.
Discovered and defined in 2014 by a team of astronomers led by R. Brent Tully at the University of Hawaii, Laniakea revolutionized our understanding of cosmic geography. Before its identification, scientists believed that the Virgo Supercluster marked the limit of our galactic neighborhood, but detailed measurements of galaxy motions and gravitational flows revealed a far more complex picture. Astronomers observed that galaxies within Virgo and many neighboring superclusters were not isolated. Instead, they were moving along vast cosmic rivers, streams of galaxies flowing together under the influence of a common gravitational basin. When these flows were mapped out, they converged toward a single center of attraction, a massive region near a cluster of galaxies known as the Great Attractor. This discovery showed that the Virgo Supercluster was not an independent entity, it was just one part of a much larger superstructure, bound together by gravity. That larger structure was named Laniakea. To appreciate its immensity, imagine this. If the Milky Way were a tiny dot on a map representing the Virgo Supercluster, then Laniakea would be the entire continent surrounding it, a sweeping expanse of galactic systems stretching across the cosmic ocean. It is not a single cluster, but a network of superclusters, each linked to the others by gravity and the cosmic web of dark matter that underpins the large-scale structure of the universe. Within its boundaries, Laniakea encompasses several major regions, including our Virgo Supercluster, the Hydra Centaurus Supercluster, and other vast galactic complexes, all drawn together into one gravitational domain. At the heart of Laniakea lies the aforementioned Great Attractor, a mysterious region located about 150 to 250 million light-years from Earth in the direction of the Centaurus constellation. Though partially obscured by the Milky Way's disk, making it difficult to observe directly, its presence is known through its gravitational influence. Thousands of galaxies, including our own Milky Way, are slowly drifting toward this region at speeds exceeding 600 kilometers per second. The Great Attractor acts as a kind of gravitational hub, anchoring the flow of galaxies within Laniakea and defining the boundaries of its cosmic domain. But even this center isn't truly a point. It's part of a larger structure itself, woven into the tapestry of the universe's filaments and clusters. The entire Laniakea supercluster spans roughly 520 million light-years, a distance so immense that even light, the fastest thing in the universe, would take 500 million years to cross from one side to the other. Within this enormous volume exist an estimated 100,000 large galaxies, each with billions or hundreds of billions of stars, along with countless smaller galaxies, nebulae, and star clusters. Altogether, the combined mass of Laniakea is thought to exceed 100 quadrillion times the mass of the Sun, a figure that boggles the human mind. And yet, even within such enormity, the universe remains mostly empty.
The galaxies of Laniakea are connected by tenuous threads of gas, dark matter, and intergalactic plasma that form the filaments of the cosmic web. But the vast spaces between these threads are immense voids, regions hundreds of millions of light years wide, where almost no galaxies exist at all. What makes Laniakea so fascinating is not merely its size, but what it reveals about the interconnectedness of the cosmos. It shows that the universe is not just a random scattering of galaxies, but a coherent structure, shaped by gravity over billions of years into a vast, flowing network. Galaxies do not simply drift in isolation, they move collectively, influenced by the gravitational pull of unseen masses, guided by the hidden hand of dark matter. Within Laniakea, our Milky Way is just one of countless travelers flowing along these invisible currents, carried through the cosmos as part of a grand galactic river. When astronomers first visualized Laniakea, they mapped the movement of galaxies like streams of water, tracing their paths toward the Great Attractor. Each galaxy's motion was plotted as a vector, a line showing its direction and velocity. When all those vectors were drawn together, a breathtaking pattern emerged. Thousands of galaxies converging toward a common gravitational well, their paths weaving a beautiful, fluid-like structure. It looked like a massive whirlpool of galaxies, a slow, swirling current spanning hundreds of millions of light years. This discovery not only redrew our cosmic map, but also gave us a new sense of belonging. It placed our Milky Way not at the center of anything, but as one small part of a vast galactic flow, drifting through the endless ocean of space. Even more remarkable is that Laniakea, as immense as it is, may not be unique. Beyond its borders, other superclusters stretch across the universe. Enormous neighbors such as the Perseus-Pisces Supercluster, the Coma Supercluster, and the Sloan Great Wall, which itself spans over 1 billion light-years. These immense structures are all interconnected, forming a kind of cosmic web, where each supercluster is a node in a vast lattice of matter. The boundaries between them are not sharp. Rather, they fade and merge, blending into one another like the edges of clouds. This interconnectedness means that even the term Laniakea Supercluster may someday be seen as just one small region of an even grander cosmic structure, whose true scale is beyond anything we can currently measure. The concept of Laniakea also carries a poetic truth. It highlights how every galaxy, including our own, is part of something unimaginably larger. Just as Earth orbits the Sun and the Sun orbits the Milky Way, so too does the Milky Way move within the local group within Virgo, and Virgo within Laniakea. It's a hierarchy of motion, a chain of cosmic relationships extending upward into infinity. The forces that govern these structures are the same ones that shape the orbits of planets and moons. It's gravity, acting on all scales, from the smallest particles to the largest formations in existence. This unity of physical law ties everything together, from our home planet to the edges of the observable universe. To put the scale of Laniakea into human terms is nearly impossible, but let's try a metaphor. Imagine shrinking the entire Milky Way to the size of a single grain of sand. In that case, the entire Laniakea Supercluster would stretch farther than the distance between major cities, perhaps hundreds of kilometers wide, filled with countless other grains of sand, each representing a galaxy. Between them would lie vast empty spaces, but each one would still be connected, moving subtly toward the same gravitational center. That's our cosmic reality, an ocean of galaxies drifting together across incomprehensible distances, all linked by gravity and time.
And yet, even Laniakea, this immense heaven, is not the final word on cosmic size. It too is just one portion of a universe that extends much farther than we can ever see. Beyond its boundaries lie other vast structures, and beyond those, the edge of the observable universe itself, 46 billion light-years in every direction. What lies beyond that edge remains unknown, perhaps infinite, perhaps part of a multiverse of unimaginable scope. But Laniakea stands as our most profound map of cosmic connectedness, a revelation that everything we see, everything that exists, belongs to one grand and graceful pattern. From the tiny orbit of our Earth around the Sun to the slow drift of galaxies across the universe, every motion, every structure, every luminous speck of light is part of this breathtaking whole.
Laniakea reminds us that the universe is not chaos. It is a vast, intricate harmony of matter and motion, a cosmic symphony that has been playing for nearly 14 billion years. It is our home in the deepest sense, not just our galaxy or our solar system, but the immense heaven that holds all of them within its embrace. As we drift outward from the immense Laniakea Supercluster, our perspective widens once again, this time to the grandest visible structure in existence, the cosmic web. It is here, on the largest scales imaginable, that the universe reveals its true architecture. When astronomers map the positions of millions of galaxies across billions of light years, a stunning pattern emerges, not a random scattering of points, but an intricate, interconnected network of threads and knots, a vast three-dimensional web stretching across all of space. The universe, it turns out, looks astonishingly like a colossal living organism. Its galaxies strung together along luminous filaments of matter, separated by enormous dark voids. This is the large-scale structure of the cosmos, the cosmic web, and it represents the ultimate framework of everything that exists. If you could somehow step back far enough to see it all at once, the universe would appear as a glowing, sponge-like mesh of light. Long filaments of galaxies crisscross to darkness, connecting dense clusters where thousands of galaxies congregate like jewels at the intersections of cosmic strands. Between those glowing threads lie vast empty regions, cosmic voids, where few, if any, galaxies exist. These voids are immense, often spanning hundreds of millions of light years across, and they make up most of the universe's volume. The web-like pattern stretches endlessly, creating a balance of light and darkness, matter and emptiness, structure and vast nothingness. It is both hauntingly beautiful and incomprehensibly vast, a cosmic tapestry woven by gravity itself. This grand structure wasn't always visible to us. For much of human history, the universe seemed uniform and simple, a scattering of stars in the night sky, perhaps dotted with the faint smudges of nearby galaxies. But as telescopes grew more powerful, astronomers began to detect structure on ever larger scales. In the late 1900s, vast galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, and the CFA Redshift Survey, began mapping the positions of hundreds of thousands of galaxies. What they discovered was revolutionary. Instead of finding galaxies distributed evenly throughout space, the maps revealed immense filaments, walls, and clusters with enormous voids between them. The universe, it seemed, had a texture, a structure as intricate as lace, as vast as eternity. At the intersections of the cosmic web lie galaxy clusters, enormous gravitationally bound systems containing hundreds or even thousands of galaxies. These are the densest knots of matter in the universe, where gravity has drawn galaxies together over billions of years. The Virgo cluster, which sits at the heart of our Virgo supercluster, is one such example. And across the cosmos, there are countless others: the Coma cluster, the Perseus cluster, and the Bullock cluster, and many more. Each cluster is like a city of galaxies, blazing with the light of billions of stars and embedded in a halo of hot gas and dark matter. These clusters are connected by filaments, vast elongated structures filled with galaxies and intergalactic gas that stretch for hundreds of millions of light years, linking one cluster to another. But for every glowing filament, there is an even larger region of darkness. The cosmic voids are the most mysterious and eerie parts of the universe. These are immense, nearly empty expanses of space, often tens or even hundreds of millions of light years across, where there are very few galaxies at all. The Bootes void, for example, is one of the largest known, spanning about 330 million light-years in diameter. Within it, there are only a handful of galaxies, so few that if our Milky Way were located in such a place, the night sky would be almost completely dark, devoid of visible stars. These voids aren't truly empty, of course. They contain thin traces of gas, dark matter, and possibly small dwarf galaxies. But compared to the dense filaments and clusters, they are regions of astonishing emptiness, a silent counterpoint to the luminous web that surrounds them. The cosmic web didn't appear all at once. It evolved over billions of years from the nearly uniform matter of the early universe. After the Big Bang, the cosmos was almost perfectly smooth,
with only tiny fluctuations in density, microscopic variations in the distribution of matter and energy. Over time, gravity amplified those small irregularities. Denser regions attracted more matter, growing larger and more massive, while the less dense areas became emptier. As this process continued, matter flowed into filaments and clusters, forming the cosmic web we see today. This flow dance of creation has been unfolding for nearly 14 billion years, transforming the universe from a mere uniform mist to a vast and intricate structure of unimaginable scale. Crucially, the cosmic web is not composed solely of visible matter. In fact, the majority of its mass is dark matter, a mysterious, invisible substance that does not emit or absorb light but exerts a powerful gravitational pull. Dark matter acts as the scaffolding of the universe, providing the framework on which galaxies form and evolve. Without it, the web would not exist. The luminous galaxies we see through telescopes are merely the glowing tips of this invisible structure, tracing the underlying skeleton of dark matter that spans the entire cosmos. Observations and computer simulations suggest that dark matter filaments thread the universe like vast cosmic highways, guiding the formation of galaxies and clusters. It's within these invisible threads that the Milky Way and every other galaxy in the universe were born. Astronomers have confirmed this intricate structure using both observation and simulation. Projects like the Millennium Simulation and the Illustris project have recreated the universe's evolution inside supercomputers, modeling billions of particles of dark matter and gas over billions of years. The results are stunning. On a cosmic scale, the simulated universe looks strikingly similar to the one we observe. Galaxies form along filaments, cluster at intersections, and leave immense voids in between. An elegant confirmation that our universe follows a consistent, predictable pattern of growth governed by gravity, dark matter, and dark energy. The resemblance between these simulations and real cosmic maps is one of modern science's most profound triumphs, offering a glimpse into the forces that shaped everything we know.
On human scales, the distances and sizes involved are incomprehensible. Each filament of the cosmic web can be hundreds of millions of light years long and several million light years thick, containing billions of galaxies. The entire observable universe may contain tens of thousands of such filaments, forming an interconnected network that spans all of space. Yet even with such immensity, the cosmic web is delicate, a faint lattice of matter suspended in an ever-expanding void. It's both monumental and fragile, the ultimate expression of cosmic order emerging from simplicity. When we think about the cosmic web, it's easy to be overwhelmed by its scale. We live within one of these filaments, our galaxy resting along a luminous strand of matter, quietly orbiting within the grand design. From our vantage point, it's difficult to imagine that this pattern continues endlessly in every direction, far beyond what we can see. Yet every telescope, every simulation, every observation confirms that it does. The universe in its largest expression is a web of light and darkness, a vast cosmic network linking everything that exists. And perhaps the most humbling realization of all is this: we are part of it. The atoms in our bodies were forged in stars that formed within galaxies, which gathered along filaments shaped by dark matter, all within the framework of the cosmic web. Every particle of matter we touch is part of this grand design. The same forces that weave galaxies together across billions of light years also hold us to the Earth, orbiting a star in a single spiral arm of galaxy. The cosmic web is not merely a distant spectacle, it is the structure of our own existence. As we move onward in our cosmic journey, we will come to the ultimate boundary of what we can see and measure, the edge of the observable universe itself. Beyond the cosmic web that we can map lies the great horizon of visibility, the limit of light's reach. And beyond that, perhaps, an infinite expanse of more webs, more clusters, more universes, stretching into eternity. But before we contemplate that infinite unknown, we must first understand what it means when astronomers speak of the observable universe, the part of this grand cosmic tapestry that our instruments and our eyes can perceive. When we take one final step back, beyond the filaments, clusters, and voids of the cosmic web, we arrive at the greatest boundary our science can define, the edge of the observable universe. It's the outermost frontier of human knowledge, a cosmic horizon that marks the limit of what we can see, detect, and measure.
Beyond it lies the unknown, a vast realm of space and time that light has not yet had the chance to reach us from. When astronomers talk about the observable universe, they mean precisely this: the region of the cosmos from which light has had enough time since the Big Bang, roughly 13.8 billion years ago, to travel to Earth. But because the universe has been expanding during that time, the true distance to those farthest regions is not 13.8 billion light years. Instead, due to cosmic expansion, the radius of the observable universe is about 46.5 billion light years in every direction. That means the entire observable universe spans roughly 93 billion light years across, a size so immense that even numbers begin to lose their meaning. To grasp this concept, we must first remember that light, the fastest thing in the universe, travels at a finite speed, about 300,000 kilometers per second. When we look out into space, we're also looking back in time. The light we see from the sun, for instance, left it about 8 minutes ago. The light from the nearest star, Proxima Centauri, takes more than 4 years to reach us. The glow from the Andromeda Galaxy has been traveling toward us for about 2.5 million years. In this way, our telescopes are also time machines. They let us see the universe as it was, not as it is. The farther we look, the older the light becomes, and the closer we come to witnessing the universe's earliest moments. Now, if the universe were static, unchanging and not expanding, the distance to the edge of what we could see would simply be how far light could have traveled in 13.8 billion years. But the universe is expanding, stretching the fabric of space itself. As space expands, distant galaxies move away from us, and the light traveling from them gets stretched as well, a phenomenon called cosmological redshift. Because of this expansion, the objects whose light we see from the early universe are now much farther away than they were when that light first began its journey. That's why the boundary of the observable universe lies about 46 billion light years away, not 13.8. It's not the age of the light that defines its edge. It's how far the universe has expanded since that light began its journey. The observable universe forms a kind of cosmic sphere centered on the observer, in our case, centered on Earth. But here's a mind-bending truth. Every observer, anywhere in the cosmos, would see their own observable universe centered on themselves. From the viewpoint of a galaxy billions of light years away, we would be near their edge of visibility. This is because there's no true center of the universe. The expansion of space happens everywhere equally, so every point in the cosmos sees itself as a center of its own observable sphere. The boundary, then, is not a physical wall or shell. It's simply the farthest distance from which light has had time to reach the observer since the dawn of the universe. When astronomers map this vast observable universe, they find structure at every scale. Closest to us are the stars of our Milky Way, followed by the neighboring galaxies of the local group. Farther out, we encounter the dense clusters and filaments of the Virgo and Laniakea Superclusters. Beyond them lie countless other galactic networks stretching in every direction, forming the immense cosmic web that fills all of space. As our view extends to greater and greater distances, we see galaxies not as they are now, but as they were billions of years ago, smaller, younger, and more chaotic. Looking outward is, quite literally, looking backward through the universe's history.
Eventually, as we peer farther still, we reach a point where we can no longer see individual galaxies. Their light becomes stretched so much by cosmic expansion that it fades into a faint glow. This faint radiation is what we call the cosmic microwave background, the afterglow of the Big Bang itself. The CMB is the oldest light in the universe, emitted when the cosmos was just 380,000 years old, long before stars and galaxies existed. At that time, the universe was a hot, dense plasma of particles and radiation. As it cooled, it became transparent, allowing light to travel freely for the first time. That light, stretched by the expansion of space for nearly 14 billion years, now reaches us as a faint microwave signal, uniform in every direction. It marks the outer edge of the observable universe, the earliest visible moment in cosmic history. What lies beyond the CMB? That's where our vision fades into mystery. Before that epoch, the universe was opaque, filled with energy so intense that photons couldn't travel freely. The period before transparency is hidden from direct view, though scientists study it through theoretical models and indirect evidence, such as the patterns in the CMB itself.
Even beyond that lies the unobservable universe, regions so distant that their light has not yet had time to reach us. Those regions exist, but they are forever beyond our observational reach, at least until cosmic expansion itself changes in some unimaginable way. The sheer size of the observable universe defies easy comprehension. It contains an estimated 2 trillion galaxies, each with billions or even trillions of stars, countless planets, moons, and clouds of interstellar gas and dust. And remember, this is only what we can see. The universe may extend infinitely beyond them, filled with countless more galaxies, perhaps with other cosmic webs, superclusters, and even regions where the laws of physics might differ from our own. Some cosmologists even propose that what we call the universe is just one bubble in an infinite multiverse, with other universes existing beyond our cosmic horizon, forever unreachable. To visualize the scale, consider this. If our entire solar system, from the Sun to the outer edge in the Kuiper Belt, were shrunk to the size of a single grain of sand, then the observable universe would still be larger than all the beaches on Earth combined. Every galaxy, every star, every planet that exists within this immense sphere of sand would fit into that cosmic ocean. Each grain a world, each handful a cluster of galaxies. And yet, even this analogy falls short because the human mind cannot truly grasp 93 billion light years. It is a scale beyond imagination, where distances and time blur together into something abstract, something purely cosmic. What's especially profound is that the observable universe is not static. It's changing every second. As time passes, light from more distant regions continues to arrive, and our observable horizon slowly expands. But paradoxically, due to the accelerating expansion of space driven by dark energy, some distant galaxies are actually moving away from us faster than the speed of light. Their light will never reach us, no matter how long we wait. Over billions of years, the observable universe will change shape. Many galaxies we can see today will eventually fade beyond our reach, disappearing forever as the expansion of space carries them away. In the far future, only the nearest galaxies, perhaps only those within our local group, will remain visible, while the rest of the universe vanishes beyond an unbridgeable horizon. So when we speak of the observable universe, we're really talking about a window in time and space, a finite portion of an infinite whole. It is both a map of the cosmos and a record of its history, a time capsule stretching from the first light of creation to the galaxies we see today. It's humbling to realize that everything humanity has ever known, every star we've ever seen, every cosmic discovery we've ever made, exists within this small glowing bubble of visibility. Beyond that bubble lies the rest of the universe, perhaps infinite, perhaps unknowable, perhaps unimaginably diverse. And yet, even knowing that we can only see a fraction of the whole, the existence of this cosmic horizon does not diminish our place in it. Instead, it deepens the wonder. We, living beings on a tiny blue planet orbiting an ordinary star, have managed to look out across almost the entire history of the cosmos, to the very edge of time itself. From our fragile vantage point, we have traced the structure of galaxies, measured the echoes of the Big Bang, and mapped the boundaries of the observable universe. It's one of the most extraordinary achievements of human curiosity, that creatures so small can comprehend something so vast. But beyond that edge, beyond the faint glow of the cosmic background, there may be far more waiting for us to discover. The observable universe is just the beginning of the story, not the end. And the next step in our journey takes us there, to the mystery of what lies beyond what we can see, into the realm of the unobservable universe, where the boundaries of knowledge give way to the infinite. When we stand on the edge of the observable universe and gaze into the cosmic darkness that lies beyond the reach of light, we find ourselves staring into one of the most profound mysteries of existence. What lies past that shimmering horizon, beyond the 46 billion light-year limit of our sight, may very well be a reality so vast and incomprehensible that even our boldest theories can only whisper hints of its truth. The universe beyond what we can see is not simply an empty void waiting to be illuminated by light that has not yet reached us. It's an entire cosmic expanse, perhaps infinite, perhaps finite but unbounded, filled with galaxies, stars, and matter just like our own corner of the cosmos, continuing endlessly in all directions. To understand what beyond the observable truly means, it helps to recall that the observable universe is not a physical edge, wall, or barrier. It's a limit of time. The light from regions farther than 46 billion light-years away hasn't had enough time since the Big Bang to reach us even at light speed, because the universe has been expanding all the while. But that doesn't mean nothing exists beyond that horizon. In fact, everything we can see is likely just a tiny fraction of the entire cosmos, perhaps as small as a drop of water in an endless ocean. Scientists are nearly certain that the universe extends far, far beyond what our telescopes can detect. The question is just how far, and whether it ever ends at all.
Modern cosmology suggests that on the largest scales, the universe appears remarkably uniform and flat. This flatness doesn't refer to being two-dimensional, but rather to the geometry of space itself. In a flat universe, the rules of Euclidean geometry hold true. Parallel lines never converge, and the sum of the angles in a triangle equals 180 degrees. If the universe had significant curvature, like the surface of a sphere, we'd detect that curvature in the way distant light bends across space. But despite decades of measurements, from the cosmic microwave background, CMB, and large-scale galaxy surveys, the evidence points overwhelmingly toward a cosmos that is almost perfectly flat. And a flat universe implies something staggering, that it could extend infinitely in all directions. If this is true, then our observable universe is merely a minuscule patch of an infinite, unending expanse, a small sphere of awareness in a cosmos that continues forever. Imagine an ant standing on a single grain of sand in a vast desert. The ant sees its immediate surroundings, perhaps a few nearby grains, but the desert stretches on endlessly beyond its vision. Our view of the cosmos is much the same. We inhabit one tiny region, surrounded by billions of galaxies, yet the grand cosmic desert may go on forever, filled with countless more galaxies, superclusters, and cosmic structures that we will never observe because their light will never reach us. This idea is both humbling and haunting. If the universe truly has no end, then there could be regions so distant that their galaxies formed under completely different conditions. In some far-off sector of space, the arrangement of galaxies might be subtly different. Stars might have formed earlier or later, and entire cosmic structures could exist that we can never imagine. And because light speed is finite while cosmic expansion is ongoing, those regions are permanently cut off from us. They exist in what scientists call causally disconnected regions, places that can never affect us and that we can never affect in return. From our perspective, they are beyond eternity. But infinity is not the only possibility. Some models suggest that while the universe may not be infinite, it is still immensely larger than the observable portion. It could be finite but unbounded, much like the surface of a sphere. On a two-dimensional globe, you can walk endlessly in one direction and never encounter an edge, even though the surface area is finite. The same could be true for our universe in 3 dimensions. It could wrap around itself in a way that if you could somehow travel far enough in one direction, you might eventually end up where you started, though cosmic expansion likely makes such a journey impossible. There are even more exotic theories that challenge our very perception of what universe means. One of the most fascinating comes from cosmic inflation theory, the idea that in the earliest moments after the Big Bang, the universe underwent an almost inconceivably rapid expansion. This inflationary burst stretched tiny quantum fluctuations into enormous structures that became the seeds of galaxies. But inflation may not have stopped everywhere at once. According to many versions of the theory, inflation continues in other regions of space even now, creating what scientists call a multiverse, an infinite series of bubble universes, each expanding independently. In this scenario, our universe, the one we see, is just one bubble in an infinite cosmic foam. Each bubble could have its own physical laws, constants, and dimensions. Some might contain universes with different forms of matter,
different strengths of gravity, or even different concepts of time and space. Others might have collapsed in upon themselves, while some could be still forming. It's an idea that stretches not just our imagination, but the very limits of what science can test. Yet it's not mere fantasy. The mathematics of inflation naturally leads to this possibility. If true, it would mean that our observable universe is just one cosmic island in an infinite archipelago of realities. Even within our own bubble, the parts beyond what we can observe may be staggeringly vast. Some cosmologists estimate that the total universe could be at least 250 times larger than the observable region, perhaps much more. Others argue that it may be infinite outright. The difference in practical terms is almost irrelevant, because both possibilities exceed our ability to explore or measure. The boundary of what we can observe acts as an eternal horizon, a cosmic curtain that no technology or future advancement can ever push beyond. We are forever enclosed within our sphere of visibility, a kind of cosmic island universe adrift in an unseeable sea. And yet, even though we can't observe beyond that horizon, the universe beyond still leaves subtle fingerprints on the world we can see. Tiny fluctuations in the cosmic microwave background, those faint temperature variations measured by satellites like COBE, WAMAP, and Planck, suggest that structures that extend far beyond our observational reach. These patterns suggest that the large-scale uniformity we see continues well past the edge of the observable universe. In other words, the cosmos doesn't abruptly end at that boundary, it simply continues, in all directions, as far as physics allows. The idea of a universe that extends forever, or a multiverse filled with countless others, is both overwhelming and strangely beautiful. It reshapes how we think about our place in reality. Every star, every galaxy, every atom that makes up you, me, and the Earth itself might be part of an infinite cosmic pattern repeating endlessly across space-time. Somewhere, unimaginably far away, there could be regions where stars never formed, or where galaxies cluster in configurations completely alien to our own. There could even be distant universes where the constants of nature are so different that life, as we know it, could never exist, and others where it flourishes under new rules of physics. Yet perhaps the most profound aspect of all is not the scale of this greater universe, but the fact that we, from our small and fragile world, can contemplate it. Our minds, limited by biology and bound by time, have managed to piece together a model of the cosmos that extends beyond what we can ever hope to see. That active imagination, backed by observation and reason, is itself a triumph of consciousness. Even though we may never see beyond the horizon, the knowledge that there is something beyond it connects us to the infinite. It is the ultimate reminder that while our vision may end, existence does not.
So, beyond the faint afterglow of the Big Bang, past the filaments of galaxies and the vast cosmic web, lies the part of the universe that remains forever hidden. Perhaps infinite, perhaps stranger than we can ever conceive. It's the realm where the laws of physics stretch toward the unknown, where other worlds, other galaxies, and maybe even other universes exist, unseen but real. The observable universe is but one shining window into this endless expanse, a glimpse into infinity itself. And though we may never cross that boundary, we can still look toward it with wonder, humility, and awe, and know that the story of the universe doesn't end where our sight does. When we speak about the number of galaxies in the observable universe, we begin to touch one of the most staggering truths in all of science, a truth that redefines what it means to be small. For a long time, astronomers believed that there might be tens of billions of galaxies scattered throughout the cosmos. But with every improvement in telescope technology, from the earliest optical instruments to the Hubble Space Telescope and now the James Webb Space Telescope, our understanding of the cosmic population has grown exponentially. Today, estimates suggest that the observable universe contains at least 200 billion galaxies, and possibly far more. Some studies even propose that there could be as many as 2 trillion. To comprehend this number, we must first remember that each galaxy is not a single object, but a vast collection of stars, planets, gas, dust, and dark matter, bound together by gravity.
Our own Milky Way, immense as it seems, is just one of these galaxies with somewhere between 100 and 400 billion stars, and countless planets orbiting them. If we were to imagine each of those 200 billion galaxies as being similar in scale, we begin to see the enormity of creation. There could be sextillions of stars, that is a number with 22 zeros, scattered throughout the cosmos, and around many of those stars are likely to be planets, moons, asteroids, and comets, forming entire systems as rich and complex as our own solar system. This vastness is not uniform, however. Galaxies vary dramatically in size, shape, and brightness. Some, like the massive elliptical galaxies, are sprawling spheroidal giants containing trillions of stars. Others, like dwarf galaxies, might contain only a few million. There are graceful spiral galaxies with arms winding outward like cosmic whirlpools, and chaotic irregular galaxies, distorted by gravitational interactions or collisions. The diversity among galaxies is breathtaking, and it tells a story of evolution, of how matter, energy, and gravity work together over billions of years to shape the universe we now see. But how do astronomers arrive at these colossal numbers? The answer begins with a small, seemingly insignificant patch of sky. In 1995, the Hubble Space Telescope performed an audacious experiment. Astronomers pointed it toward a tiny region of space, an area no larger than a grain of sand held at arm's length, and let it collect light for many days. The result was the Hubble Deep Field, one of the most transformative images ever taken. In that minuscule patch of darkness, Hubble revealed nearly 3,000 galaxies, some so faint that their light had been traveling toward us for over 13 billion years. From that single image, astronomers extrapolated that the entire sky must contain hundreds of billions of galaxies. Later, the Hubble Ultra Deep Field and Extreme Deep Field looked even deeper, pushing back to the very limits of the observable universe. Each time, new galaxies appeared, smaller, fainter, more distant, like whispers from the dawn of time. Then, with the arrival of the James Webb Space Telescope, JWST, humanity's cosmic vision expanded again. Webb's infrared sensitivity allows it to peer through cosmic dust and see even older galaxies, some formed just 300 million years after the Big Bang. These young, primitive galaxies are small, compact, and chaotic, providing clues about the earliest stages of cosmic evolution. However, even with these instruments, we are still only scratching the surface. Many galaxies are too faint or too far away to be detected by any current telescope. Their light has been stretched to wavelengths beyond what we can observe, and some are hidden behind the glare of near stars or clouds of cosmic dust. So the 200 billion figure is likely a lower bound, a conservative estimate based on what our technology can currently detect. As our observational tools improve, as we build even more sensitive telescopes like the upcoming Nancy Grace Roman Telescope and Extreme Large Telescope, we may discover that the true number of galaxies is far greater, perhaps in the trillions. The distribution of these galaxies is also a marvel of cosmic order. They are not sprinkled randomly through space, but arranged in immense patterns, clusters, filaments, and walls that form the grand cosmic web. In between these structures lie enormous voids, regions where few galaxies exist at all. Some clusters contain thousands of galaxies bound together by their mutual gravity, while others float alone, isolated in the silent stretches between the filaments. This structure is the universe's fingerprint, a map of how matter has evolved since the Big Bang, guided by the invisible scaffolding of dark matter and driven by the mysterious force of dark energy that accelerates the expansion of space.
Within these 200 billion galaxies lies an unimaginable diversity of environments. Some galaxies are bustling with stellar nurseries, where vast crowds of gas collapse under gravity to form new stars. In others, star formation has long since ceased, leaving only old, dying suns and the faint glow of ancient light. Many harbor supermassive black holes at their centers, some billions of times more massive than our sun, shaping the galaxies around them through their immense gravitational influence. When matter falls into these black holes, it releases titanic amounts of energy, creating quasars and active galactic nuclei that outshine entire galaxies. If every galaxy has hundreds of billions of stars, and many of those stars host planets, the numbers begin to reach truly cosmic proportions. Current estimates suggest there may be as many as 10 to the power of 24 planets in the observable universe. That's one followed by 24 zeros. Even if only a tiny fraction of those planets are habitable, the potential for other forms of life becomes not just possible, but statistically likely. Somewhere across this sea of galaxies, there could be civilizations looking up at their own night skies, wondering the same thing we do. How vast is the universe, and are we alone in it? This understanding has transformed how we see ourselves. Once, we believed that Earth was the center of everything, the fixed point around which the heavens revolved. Then we learned that we orbited the Sun, and that the Sun was just one of billions of stars in a galaxy. Now we know that our galaxy itself is just one among hundreds of billions, possibly trillions. Each time we've expanded our perspective, we found that we occupy a smaller and smaller part of the cosmos, and yet paradoxically, our understanding grows larger and more profound. The idea of 200 billion galaxies, each a world of worlds, is difficult for the human mind to fully comprehend. We can say the number, we can calculate it, but to truly grasp it is impossible. Our imaginations simply cannot stretch that far. And yet, in a way, that's what makes it so powerful. The sheer scale of it humbles us, but it also uplifts us. It reminds us that the universe is not small or empty, it is overflowing with possibilities, with stars and worlds, with light and mystery. Every point of light we see in the night sky belongs to just one galaxy, our own. Beyond that, in the darkness between the stars, lie the faint glows of countless others, each one a cosmic city of suns. The Hubble Deep Field shows us that even in the darkest parts of space, if you look closely enough, light is everywhere. The universe is filled to the brim with galaxies, each a story of creation, destruction, and renewal playing out over billions of years. So when we say the observable universe contains 200 billion galaxies, we're not just quoting a statistic, we're acknowledging a profound truth about existence. We're surrounded by abundance beyond measure. The cosmos is not a cold, empty void. It is a vast, dynamic ocean of light and life and possibility. And within that grand expanse, our own small world, orbiting an ordinary star in an unremarkable galaxy, becomes all the more precious, a single spark in a boundless sea of stars. When we try to comprehend the true scale of the universe, even numbers begin to lose their meaning. Billions and trillions sound enormous, but after a certain point, they blur into abstraction, quantities too large for the human mind to genuinely imagine. So to bring this unimaginable vastness down to a level we can at least begin to grasp, let's try something different. Let's put it in perspective. If the Milky Way galaxy, our entire galactic home, with its hundreds of billions of stars and its 100,000 light-year diameter, were reduced to the size of a single grain of sand, then the observable universe would stretch as wide as a beach thousands of miles long. Picture that for a moment. One tiny grain, resting in your hand, representing everything we know, the sun, the earth, the countless stars of our spiral arms, all condensed to that speck. And then imagine an endless coastline stretching far beyond the horizon, with trillions upon trillions of other grains of sand. Each grain is another galaxy, each containing its own billions of stars, worlds, and perhaps even life. That is how vast the cosmos truly is. This comparison captures only a hint of the enormity. A single grain of sand is almost too large to symbolize our galaxy. The Milky Way's disk alone spans about 100,000 light-years, and the universe, as we can observe it, extends some 93 billion light-years across. That means if you were to travel from one edge of the observable universe to the other at the speed of light, 300,000 kilometers per second, it would take you 93 billion years to make the journey. And yet, that's just the portion we can see. The universe may continue infinitely beyond that, far past what any grain of sand or metaphor could describe. But let's linger on this image, the grain and the beach, because it helps us sense both the beauty and the humility of our place in the cosmos. if every galaxy is a grain of sand, then the universe isn't merely a beach. It's more like a planet-sized desert, a sea of infinite sand dunes stretching in every direction. Each grain glitters faintly under the sunlight, a symbol of a galaxy shining in the cosmic night. To think that within one of those grains, within our own Milky Way, lies the Earth, a tiny planet orbiting a single average star, is to recognize just how minuscule we truly are in the grand design. Now imagine walking along that beach. Each step you take might represent billions of light years. The grains beneath your feet are galaxies, some small and dim, others bright and massive. In a single handful, you might hold thousands of galaxies, an entire supercluster compressed in your palm. And then as you drop that sand, more appears in its place, stretching endlessly beyond sight. Even if you could count grains of sand as fast as the blink of an eye, you would never reach the end. That is what it means to live in a universe that is both finite in what we can observe and potentially infinite in reality. Astronomers often use metaphors like this not to exaggerate, but because words and numbers alone simply can't convey the immensity of the cosmos. We live on a world that seems vast to us, where oceans span thousands of kilometers and planets orbit at immense distances. But on a galactic scale, our solar system is smaller than a speck of dust in a cathedral. The entire Milky Way, filled with stars and nebulae and black holes, becomes a mere grain among hundreds of billions. When you look up at the night sky and see the faint band of the Milky Way stretching across the darkness, remember, you're not just seeing stars, you're looking through the plane of that single grain of sand in an infinite beach of galaxies.
Even light, the fastest thing in existence, struggles to cross this immensity. Light that began its journey when dinosaurs still walked the Earth has only just arrived from nearby galaxies. Light from the farthest galaxies we can see has been traveling for more than 13 billion years, crossing expanding space, stretched and redshifted as it comes. Each photon of that ancient light carries with it a message, a story from the dawn of time, whispering across the void to tell us what the universe once was. The enormity of this cosmic beach also transforms how we view our own significance. Some might feel diminished by it, seeing in the scale of the universe a reminder of how small and fragile human life really is. But there's another way to see it, not as a tale of insignificance, but of wonder. Because among all those countless grains, we are one of the few that knows it exists. We are part of the universe that has become conscious of itself, able to look out across billions of light years and comprehend its own vastness. In that sense, our smallness does not make us meaningless, it makes us miraculous. Think of what humanity has achieved. From standing on the surface of a single planet, we have measured the distances to galaxies billions of light years away, mapped the shape of the cosmos, and even captured the faint glow left over from the Big Bang itself. Our species has existed for only the briefest flicker of cosmic time, and yet we've managed to chart a portion of infinity. The grains of sand we can see, the galaxies mapped by Hubble and Webb, are the visible evidence of our curiosity reaching outward one photon at a time. To drive this image home, imagine shrinking not just the Milky Way, but everything else along with it. The solar system would become smaller than an atom inside that grain of sand. The sun would be far too tiny to see. Earth, our entire world, would be so small that it wouldn't even exist in comparison. A subatomic mote within a subatomic mote. And yet, it's here, on this microscopic world within a speck of cosmic dust, that love, music, science, art, and thought have all arisen. All the history of humanity, every civilization, every act of creation has taken place within that imperceptible dot. And so when we compare the Milky Way to a grain of sand and the universe to an endless beach, we aren't just using poetic language. We're trying to describe something that is both physically real and emotionally overwhelming. The sheer disproportion between what we are and what we are part of. That contrast is what makes astronomy not just a science, but a philosophy.
It asks us to confront both our insignificance and our significance simultaneously, to accept that we are small, but also that our smallness exists within something unimaginably grand. Even now, as telescopes peer deeper into space, each new discovery adds another grain to the cosmic beach. And every time we find a new galaxy, a new exoplanet, or a new mystery in the dark, we're reminded that the beach has no end. The more we learn, the larger it becomes. An endless shore stretching farther than the mind can reach, sparkling with the light of 1 trillion suns. So next time you stand on an actual beach, pick up a handful of sand and let the grains fall through your fingers. Remember that each grain could represent an entire galaxy, complete with stars, worlds, and perhaps even beings wondering the same thing you are right now. Look out at the horizon, that faint line where sky meets sea, and know that in every direction, for billions of light years, the universe continues, vast and beautiful beyond measure. In that simple, humbling moment, you will feel it, the delicate balance between the infinite and the infinitesimal, between the cosmic and the human. And that's the perspective that changes everything. To realize that even though we are but one grain in an eternal beach of galaxies, we are a grain that can see the shore, that can wonder, and that can dream about what lies beyond. When we begin to contemplate the scale of the universe, from the tiny world beneath our feet to the immense expanse of galaxies stretching across billions of light years, we inevitably run into a profound limitation: the boundaries of the human mind. Our brains evolved for navigating forests, hunting prey, and building shelters. Were never designed to comprehend distances measured in trillions of kilometers or timescales spanning billions of years. We can describe these numbers, write them down, even visualize them abstractly, but to truly feel them, to internalize their enormity, is something no human consciousness can fully achieve. It's not just big, it's beyond imagination. When we say that a light year equals 9.46 trillion kilometers, the number alone loses all intuitive meaning. We can picture a kilometer, perhaps even 100, but beyond a few thousand, the scale begins to dissolve into abstraction. Our mental imagery collapses under the weight of such magnitude. A light year doesn't feel like a measurable distance. It feels like an idea, an intellectual construct that sits somewhere outside ordinary experience. And yet, light years are the basic units of the cosmos, steps along a cosmic ruler so vast that even the shortest measurements exceed the boundaries of our comprehension. Consider the distance between Earth and the Sun, about 150 million kilometers. That's already difficult to grasp. Now stretch that 270,000 times and you've traveled 1 light year. To cross the Milky Way, you'd need to cover 100,000 of those. And that's still nothing compared to the span of the observable universe, which stretches 93 billion light-years in diameter. These numbers exist far beyond the scale of our senses. Our neurons cannot translate them into something tangible. No mental imagery, no metaphor, no analogy can truly convey what such distances mean. The same is true for time. Our lifespans, decades at most, are mere flickers in the cosmic timeline. Human history, stretching back tens of thousands of years, barely registers against the 13.8 billion years since the universe began. The rise and fall of civilizations, the building of pyramids, the invention of writing, all of it has occurred in less than a heartbeat of cosmic time. The entire history of our species is smaller than a pixel on the universe's clock. When we talk about stars forming billions of years ago or galaxies colliding billions of years in the future, our words remain detached from any lived sense of time. We can say billion years, but we can't truly feel it. Our perception evolved for the immediate and the local, for recognizing a friend's face across a field, for remembering where fruit trees bloom in a particular season, for calculating the distance to a nearby mountain or river. Even the concept of a planet is alien to our natural intuition. We only know the shape and scale of Earth because we've measured it, not because we can sense it. To the human brain, the horizon is the limit of the world. Beyond that, abstraction begins. And yet through science and imagination,
We've stretched that horizon to encompass galaxies billions of light years away. But the cost of that expansion is a sense of cognitive vertigo, a dizzying realization that the universe operates on scales we cannot meaningfully imagine. When we try to visualize the Milky Way's 400 billion stars, we might picture dots of light scattered across a black canvas. But even that is deceptive, because each dot in such a mental image would be separated by vast oceans of emptiness. The Milky Way, magnificent as it is mostly space. Space so empty that if our sun were the size of a grapefruit, the nearest star, Proxima Centauri, would be another grapefruit 4,000 kilometers away. Between them, nothing but darkness. Our galaxy's spiral arms, glowing with stars, are still mostly void. The beauty of the night sky hides how thinly spread its light truly is. And when we take that emptiness and multiply it by 200 billion galaxies, each separated by millions of light years, the limits of comprehension crumble entirely. The mind cannot hold such scale. It buckles under the enormity of it. What remains is awe, not the awe of understanding, but the awe of recognizing that something is beyond understanding. It is the same feeling ancient humans must have felt when they first looked up at the stars and realized that the heavens were vast and unreachable. That sense of smallness, of standing before something infinite, has never left us. It has only deepened.
Even visualization, our most powerful tool for grasping the abstract, fails at this level. Astronomers create maps and simulations of the universe, digital models showing filaments, clusters, and cosmic voids. These help us see the large-scale structure of the cosmos, but they are still simplifications, compressing incomprehensible distances into something the human eye can interpret. When we watch these simulations, it's easy to forget that each glowing dot might represent an entire galaxy, each one with billions of suns. The maps are not the territory. They are shadows of something too vast to render in full. And yet it's precisely in confronting this incomprehensibility that we find meaning. Our inability to fully understand does not diminish the wonder, it amplifies it. The fact that our small, finite minds can even conceive of infinity, can even ask about what lies beyond the observable universe, is extraordinary. The human brain, weighing barely a kilogram and composed of the same elements found in distant stars, has evolved to think about the universe that birthed it. That we can calculate the age of galaxies, trace the origin of elements, and model the birth of space and time itself is, in a way, a kind of miracle. Still, we are limited. We rely on metaphors, grains of sand, oceans, beacons of light to make sense of what cannot fit inside the boundaries of thought. These metaphors are beautiful, but they are also reminders of how small our perspective is. The universe is not built for human comprehension, it simply is. And yet, our need to understand, to reach beyond the possible, is what defines us. We build equations to measure infinity, telescopes to see back in time, and languages to describe the indescribable. We are, in essence, creatures of wonder, beings who live in a universe far too large to understand, but who can't help trying anyway. And that striving, that unending effort to comprehend what cannot be comprehended, is perhaps the most human thing of all. It is what drives science, art, and philosophy alike, the yearning to bridge the gap between what we can know and what we can only imagine. The struggle to comprehend the universe is not a failure, it is an expression of our deepest curiosity. The challenge itself is the gift. Because even if our minds cannot truly hold the scale of the cosmos, they can feel its immensity. They can look up at the stars and sense, deep within, that we are part of something vast and ancient and mysterious. And that feeling, that mixture of awe, humility, and wonder, is how we touch the infinite, even from within the confines of our finite minds. For all our limitations in grasping the sheer magnitude of the cosmos, humanity has never stopped trying to see further, to reach beyond what once seemed unreachable. That impulse to explore, to discover, To look outward has driven some of the most profound achievements in our history. Over the past century, we've gone from barely knowing that other galaxies existed to mapping billions of them. We've transformed pinpricks of light in the night sky into windows into the distant past. And at the heart of that revolution are our telescopes, our eyes into the universe, with names that have become synonymous with exploration: Hubble and James Webb. The Hubble Space Telescope, launched in 1990, was one of humanity's most transformative tools. Floating silently in Earth's orbit, above the blurring effects of our atmosphere, Hubble began capturing the cosmos in exquisite detail, light unfiltered, pure and ancient. What it gave us wasn't just clearer images, it reshaped our understanding of existence itself. Before Hubble, astronomers estimated that the universe contained tens of billions of galaxies. After Hubble's deep field and ultra-deep field observations, where it stared at seemingly empty patches of sky for days and weeks at a time, it revealed thousands of galaxies in regions smaller than a grain of sand held at arm's length. Each one was a distant world of stars and potential planets. That discovery alone implied that the observable universe might contain hundreds of billions, perhaps even trillions of galaxies. Hubble showed us that what once looked like void was in truth filled with light. And yet, as profound as Hubble's discoveries were, they were only the beginning. In December 2021, humanity launched a successor, not merely an improved telescope, but an entirely new kind of observatory. The James Webb Space Telescope, WST, was designed to peer deeper into space and further back in time than any instrument before it. Unlike Hubble, which primarily observes invisible and ultraviolet light, Webb specializes in the infrared spectrum. This allows it to see light that has been stretched by billions of years of cosmic expansion. Light so ancient that it carries the story of the universe's earliest galaxies.
Webb's golden mirrors, each hexagonal and precisely engineered, unfold like the petals of a cosmic flower, capturing faint glimmers of light that have traveled across 13 billion years of time. What Webb sees isn't just beauty, it's history. Every image is a time machine, revealing galaxies as they were when the universe was only a few 100 million years old, long before our sun, our solar system, or even our Milky Way existed. In a sense, when we look at Webb's images, we are peering into the infancy of everything we know. The discoveries have already been breathtaking. Webb has found galaxies that challenge our understanding of when and how such massive structures could have formed. Some of these ancient galaxies appear to have formed far earlier and grown much larger than our current cosmological models predicted. It's as if, just when we thought we had begun to understand the universe's timeline, Webb has reminded us that the cosmos still holds secrets deeper than our theories can reach. Beyond distant galaxies, Webb is also studying exoplanets, worlds orbiting other stars, by analyzing their atmospheres. By capturing faint signals of light as planets pass in front of their suns, Webb can detect the chemical fingerprints of gases like carbon dioxide, methane, and even water vapor. These are the ingredients for life as we know it, and each discovery brings us closer to answering one of humanity's oldest questions: are we alone? But perhaps the most extraordinary thing about these telescopes is not just what they see, but how far they allow us to feel connected to the universe. The light that Hubble and Webb capture has traveled across unimaginable distances and times. Some of it began its journey long before Earth even existed, passing through the birth and death of countless stars, through the expansion of space itself, until finally striking a mirror orbiting a small blue planet. When scientists process that light into an image, it is as if the universe itself has whispered across eons just to tell us its story. Each new telescope, each new image, expands not only our knowledge, but also our sense of scale. We are mapping the structure of the cosmos in ever greater detail, tracing how galaxies cluster together into filaments, how dark matter shapes the skeleton of the universe, and how gravity weaves everything into the great cosmic web. And yet, with every discovery, our questions multiply. For every mystery solved, 10 more appear. Why does the universe expand faster than our equations predict? What is the true nature of dark energy, that invisible force driving the cosmos apart? What lies beyond the observable horizon? In this way, telescopes are not merely scientific instruments. They are symbols of human curiosity, proof that even in a universe of overwhelming scale, we dare to reach beyond our grasp. Each generation of astronomers builds upon the work of those who came before, pushing our perception outward layer by layer. The humble lenses of Galileo's time, once aimed at the moons of Jupiter, have evolved into floating observatories that can see across billions of light years. It's a testament to how far our desire to understand can take us. And it's not stopping. Plans are already underway for the next generation of telescopes that will go beyond even Webb. The Nancy Grace Roman Space Telescope, expected to launch later this decade, will survey vast portions of the sky with unparalleled precision, studying the mysterious forces shaping cosmic expansion. On the ground, the extremely large telescope in Chile and the 30-meter telescope in Hawaii will give us even sharper views of galaxies and exoplanets, their enormous mirrors gathering light from the faintest corners of the universe. Together, these instruments will continue to peel back the layers of cosmic history, turning the unknown into the known, one photon at a time. What's remarkable is that all of this, every discovery, every breathtaking image, originates from the same small planet orbiting an average star on the outskirts of a single galaxy. From this tiny speck, we've managed to send our eyes into the heavens and see across the breadth of space and time. We have become, in Carl Sagan's words, a way for the cosmos to know itself. Through Hubble, Webb, and the instruments yet to come, the universe is reflecting upon its own creation, revealing its story to one of its smallest, most curious inhabitants.
And perhaps that's the most poetic truth of all. In exploring the cosmos, we are also exploring ourselves, our hunger for knowledge, our courage to confront the infinite, and our ability to find meaning even in the immensity of space. Each image captured by our telescopes is more than just light from afar. It's a mirror showing us what it means to be human, to wonder, to reach, and to never stop seeking. As we come to the end of this journey across the cosmos, we are left standing in a place that feels both impossibly small and infinitely vast at the same time. We began by asking a simple question: how big is the universe compared to our galaxy? And we've traveled from the spiraling arms of the Milky Way to the edge of the observable universe itself. Along the way, we've encountered stars separated by light years, galaxies spanning hundreds of thousands of light years, and superclusters stretching across hundreds of millions. We've seen the cosmic web, the universe's grand architecture, and peered into the depths of time through the eyes of telescopes like Hubble and Webb. And now as we look back at all we've uncovered, a profound truth emerges. We are incredibly small, almost vanishingly so. Yet we are capable of comprehending the vastness that dwarfs us. To realize this is to feel a kind of sacred humility. Our entire existence, every mountain, ocean, city, and thought, exists on a tiny blue planet orbiting an average star, itself just one among hundreds of billions in a single galaxy. And that galaxy is but one among hundreds of billions more. If you zoom out far enough, Earth disappears entirely, swallowed by the infinite darkness between stars. Even our galaxy, magnificent as it is, becomes a faint smudge of light, lost in the endless sea of cosmic structures. On the scale of the universe, we are less than dust. And yet, here we are, aware of it all. That awareness is something extraordinary. The universe, which seems so cold, vast, and indifferent, has produced within itself something capable of wondering about it. Us. We are made of atoms forged in ancient stars, particles that have drifted through billions of years to come together in a form that can look up and ask, what am I a part of? When we gaze at the night sky, we are not just observing light, we are witnessing our own origins. Every star is a reminder that the elements in our blood, our bones, and our breath were born in the hearts of long-dead suns. We are literally the universe becoming conscious of itself. It's astonishing to think that on this tiny planet, orbiting one ordinary star, life arose, fragile, fleeting, and yet curious enough to reach across the void. In just a blink of cosmic time, we have gone from cave paintings to space telescopes, from wondering if the stars were holes in a dark sky to measuring the afterglow of the Big Bang. We've stretched our perception from the subatomic to the intergalactic, mapping not only where we are, but when we are, tracing the story of existence itself from the first flicker of light to the vast expanse we see today. And even though we are small, our smallness doesn't diminish us. It gives our existence depth. In a universe that spans billions of light years, meaning is not handed to us. We create it. We give it form through art, science, love, and curiosity. We build telescopes and poems from the same human drive, the desire to reach beyond ourselves, to touch what lies beyond the horizon. That yearning connects us to something timeless. It's the same spark that led ancient astronomers to chart the stars, and modern scientists to send machines beyond our solar system. Every act of curiosity is an act of defiance against the vastness that might otherwise make us feel insignificant. The more we learn, the more the universe transforms from a distant mystery into a shared home. We realize that we are not separate from it. We are expressions of it. The hydrogen in our bodies was created in the Big Bang. The calcium in our bones was forged in dying stars. The iron in our blood was born from the explosions of supernovae. Every heartbeat, every breath, every thought is part of a story that began nearly 14 billion years ago. When you look up at the stars, you are not looking at something out there. You are looking at a reflection of what you are made of. And this realization, this moment of awe, is where science and wonder meet. We often think of the universe as something to be measured and explained, but it is also something to be felt. It humbles us, but it also uplifts us. It reminds us that even though we are small, we are capable of perceiving beauty on a cosmic scale. When we see the faint light of a galaxy billions of light years away, we are bridging both space and time. We are hearing the echo of creation traveling across the universe to reach us, fragile beings made of stardust standing beneath the sky. Perhaps that's the true gift of the cosmos, not just its vastness, but the fact that we can sense our place within it. To know how tiny we are, and yet to still feel wonder, is to be fully human. It's to look into infinity and not be crushed by it, but inspired. It's to understand that the same forces that shape galaxies also flow within us. The gravity that binds stars also binds our feet to the earth. The light that began billions of years ago now falls softly onto our eyes. We are not observers standing outside the universe. We are the universe observing itself.
In the end, perhaps that is the most beautiful paradox of all. We are specks of dust, adrift in a vast cosmic ocean. And yet, within us burns the light of understanding, the spark of curiosity, the courage to ask questions that stretch to the edges of time. We may never grasp the full scope of the universe, but that's not what matters. What matters is that we try, that we keep looking up, keep wondering, keep reaching beyond what we know. Because somewhere out there, in the darkness between galaxies, the story continues. A story of creation, of light, of mystery. And here we are, part of that story, able to witness it, to feel awe, and to know that against all odds, the universe has found a way to see itself, through us. So as you look up at the night sky, remember this. You are not small because you are part of something vast. You are vast because something infinite has come alive within you. The stars above are not distant strangers. They are family, connected to you through the same cosmic thread that weaves everything together. You are a child of the universe, and the light that fills the heavens also fills you. And that, in the end, is the wonder of it all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.